remember this, Nash equilibrium does not give the best possible outcome for everyone. That is not what is happening. If you think about it, both players remaining silent would be in some sense a good outcome for everyone. But Nash equilibrium does not give that. Nash equilibrium gives the most stable outcome. It gives the outcome where no player changes from what they are currently doing. And if both players were to remain silent, that would provide an incentive to other player to change the strategy. So this game is being played, and it is denoted by the tuple of strategies and a payoff, which is the most important part of the game in some sense. It represents the numerical reward that each player gets based on the strategies of everyone else. So that is typically denoted by U based on all the strategies of others. So a very key idea in formalizing or thinking about Nash equilibrium is the idea of a best response. So what is a best response? A best response is a strategy which produces the most favorable outcome for a player given the strategies of other players. So you can think of it as your best strategy. It is a strategy that gives you the highest payoff, that gives you the highest reward given what others are doing. So, and this is a key concept in formalizing and also understanding the idea of a Nash equilibrium. So we'll understand the idea of a best response through it is not very clear what a Nash equilibrium here would be. So we consider the idea of a best response. Let us assume that the penalty shooter assumes that goalkeeper dives to the left. He can go to the left with probability half and right with probability half. So let us calculate what would be the expected reward. What would be the reward in expectation that shooter would get with each strategy. So let's say if shooter chooses to go up always.
Ask the audience if they know anything about expectation.
Do you know expectations are the idea of an expectation? Everyone is comfortable with expectations? Okay, fine. So expected reward is just. So expected reward for up against a strategy of half-half for the goalkeeper would be, he would get half of the times a reward of 5 and half of the times a reward of 0. So the expected reward would be 2.5. Similarly for middle, he would get 2.5. And for down, he would get a reward of 3. So in this case, if you look at it, the expected reward is the highest when the shooter decides to go down. Now, this was with probability half. We can do this kind of modeling for all different beliefs that the shooter may have about the goalkeeper diving to the left or the right. And that is represented by the idea of a best response diagram. So, it might look complicated, just stay with me. A best response diagram can be represented this way. On the x-axis you have probability of the goalie going right, the left extreme being the probability 0 and right being 1. And then you just find the expected payoff. So here we are writing expected payoff as the probability function. Earlier we had just half. Now we have as a function of probability of r. So what you can see is if you write the expected payoff for each of the strategies of the goalie, then you see that this upper half, this upper envelope of this diagram represents the best response. So if the belief is this, then before the probability of x here, the shooter should always go for up. In this region, in the middle, the shooter should always go for down. And in this region, the shooter should always go for middle. These are the best responses. These are the responses that maximize the payoff for the shooter. Mathematically, we can represent it this way, that it is the expected SI is the best response to strategy of other players if the reward or the expected reward is the highest. So now we can formalize the definition or think about Nash equilibrium in another way. A Nash equilibrium is the strategy where each player plays the best response to the strategy of other players. So how do the two definitions connect? Think about it this way. What did we define Nash equilibrium earlier? A Nash equilibrium represents a state when no player has an incentive to unilaterally deviate from that point. So if no player has an incentive to deviate, what they are currently playing is already good enough for them. They cannot do better by deviating. So in a sense, it is already a best response to what other players are playing. And since that is true for each of the players, you can think of a Nash equilibrium as a state where everyone is playing a best response to everyone else's strategies. So you get the idea that this in some sense represents an equilibrium. Everyone is playing the best that they can do. So in the game of prisoner's dilemma, both players confessing is actually a best response to the strategy of other players. So we look at another game. It is known as the Battle of Sexes. A man and a woman wish to meet, but they have to choose between a boxing fight and a shopping. So man prefers the fight and woman prefers shopping, but both prefer to stay together. So the payoff matrix for such a game could be written this way. So if both of them go for boxing, the man has a payoff of 3, woman has a payoff of 2. If man goes for boxing, and woman goes for shopping, there is 1, 1. Then here there is 0, 0. And then there is 2, 3. Now, would anyone like to guess what are the Nash equilibrium here? What is the Nash equilibrium here? Any guesses? Yeah, that's a very good, that's actually the correct answer. So and see, the man has no incentive to deviate from boxing, because in that case, if woman is going for boxing, he will get 0, 0, he will get a 0 payoff. Also the woman does not have any incentive to switch from boxing to shopping, because she will get a payoff of 1. Similarly, in the shopping we can see that no one has an incentive to deviate. So here, as we see, that there are 2 Nash equilibriums. So you might have thought that there is a unique Nash equilibrium. That may not be the case. There are games where there are more than 1 Nash equilibrium. So as you correctly said, boxing and shopping and shopping are the 2 Nash equilibriums. So let's look at another game. It is known as the game of matching pennies. There are 2 players and they choose heads or tails. Player 1 wins if the choices match up, and player 2 wins if the choices differ. So we can represent the payoffs through this way. Like if they match up, then player 1 gets heads and player 1 gets 3 and player 2 gets 1. And if they differ, player 2 gets 3 and player 1 gets 1. So in this case, can you see, do you think there is a Nash equilibrium, or is there a Nash equilibrium? No, right? Because if you look closely, if player 1 goes for heads, then player 2 would want to go for tails. And if player 2 is going for tails, player 1 would want to go for tails. But if player 1 is going, and you see this back and forth, there is no stable point where you are converging. You keep on switching all the time. So you can see that there is no Nash equilibrium and everyone wants to deviate. So what is the solution here? How can we find an equilibrium point here? So the idea is to randomize their choices according to a distribution over the strategies. And this brings us to the idea of mixed strategies. So what are mixed strategies? A mixed strategy is a strategy that assigns probability to pure strategies. Each player selects a particular strategy with some probability. So mathematically it can be represented as a tuple x1, x2, xn, where each act with xi represents the probability of selecting action I. So we'll see that it's a very powerful concept. So consider this game. Now we look again at the game of matching pennies. Suppose player 1 chooses heads with probability half. Then claim that no matter what player 2 chooses, the expected payoff remains the same. So see, if the expected payoff for player 1, if he chooses heads against the other player choosing half, would be half times 3 plus half times 1, which would be 2. And the expected payoff from tails is also 2. So the payoff from any mixed strategy of the 2 will also be 2. So whatever he chooses, it does not matter. The expected payoff remains the same. And if both players choose heads and tails with half and half probability, they have no reason to deviate. They cannot get a more payoff than deviating, because in any case you would get an expected payoff of 2 only. So that is a Nash equilibrium. And from our best response idea, we see that since you cannot do better than an expected payoff of 2, and you are able to achieve 2 with your strategy of playing half heads and half tails, it is already a best response. So both players playing heads and tails with half is a best response to each other's strategies, and so we are in a Nash equilibrium. So I want you to remember this about Nash equilibrium. Nash equilibrium emphasizes the idea of stability. It is a point where nobody wants to deviate unilaterally, nobody wants to change their strategies alone. Also, it is a condition where each player's strategy is already a best response. It maximizes the best given what other players are doing. And a very key idea is that it is a no regret strategy. If you were to look back and if you were to think, given what other players did, would you like to change your strategy? And the answer would be no, because you were already doing the best you can. And so that is the idea of a mixed strategy Nash equilibrium. And you can represent it mathematically, that a mixed strategy profile is x1, x2, x star. If for each player xi star is the best response to xi minus star, and xi is the mixed strategy for each player. So there is a very famous result of John Nash where he proved that every 2-player game has at least one possibly mixed Nash equilibrium, and this was proven, I think, in 1950. So now we come to the core idea of this talk. that we know that Nash equilibrium exists, and for some games we found one. But that was a guess and check method that we did we just manual reasoning, and that may not scale very well for bigger games. So how do we find a systematic way to compute Nash equilibrium? And there comes the beautiful algorithm of Lemke-Hausen. Lemke-Hausen was an algorithm that was introduced in 1964 by Lemke and Hausen, and it was the first constructive algorithm that is based on the idea of pivoting, that gives you the strategy, that gives you a method to find Nash equilibrium constructively for any biometrics games. So a biometrics game is, there are n strategies for player 1 and m strategies for player 2. So it is also said to be the best known among the combinatorial algorithms for Nash equilibrium. It is so good that even modern solvers, even after so many years, use Lemke-Hausen to compute Nash equilibrium. So to illustrate the idea of Nash equilibrium, I'll hand it over to Pratham.
So, as was just said, Lemke-Hausen is an algorithm to find Nash equilibriums in biometric games. So, what are biometrics games? Biometrics games are what we have seen till now. They are two-player simultaneous games. That is, both player makes decision at the same time, or like unknown to each other, and then they have payoffs. So, in general, if like player 1 has m strategies and player 2 has n strategies, we can write off a payoff matrix in such form. Now observe this, that if we take all the first elements of this matrix and make it a like separate matrix A, and similarly we take the second elements of tuple and make a B matrix, these ith and j, like ij element of this matrix represents a payoff for player 1 if player 1 chooses the action I and player 2 chooses the action j. And this allows us to write our like equations very efficiently. So like as we have seen earlier, mixed strategies are vectors of like probability distribution over all the possible strategies, and we can write the expected payoffs in a very nice fashion this way. So this opens up to form summation over I and j, a ij, xi and yj, which is basically the expectation if you open it. And finally we can write off the Nash equilibrium in terms of these equations as it is the mixed strategy x star and y star, for which the expected payoff under x star y star is greater than all other expected payoff for every x, keeping the y star constant, and similarly for keeping x star constant y.
This should be X star.
Yeah. So now let us illustrate Lemke-Hausen algorithm for matching pennies, which we have seen earlier. So I am writing the payoff matrix in a bit like different fashion. So I have given labels to these strategies. So player 1 choosing head is now labeled 1, choosing tail becomes 2, and player 2 choosing head becomes 3 and 4. We'll use these labels later, so that's why I have used them, but it's quite intuitive. So this is the best response diagram as we have seen earlier. And so now the idea behind Lemke-Hausen algorithm is that we create a polytope and then we search on its boundary for some points. So to first create a polytope, we'll take the upper envelope and we'll take the region above it. So this is for two-dimensional diagram, but even in n dimensions we'll have a n dimension polyhedron.
Question.
Yeah.
Define polytope.
So for right now it's not like necessary to go. I have the mathematical definition in next slide, but yeah. So here this region can be like the useful region to us can be seen in this fashion, that it is like it is space over all the strategies, mixed strategies and values, so that like it is a valid strategy, and the payoff under that strategy, the maximum payoff under that strategy is lower than this. So for a general matrix it comes out to this, that x is like for the 2D matrix it comes out like x is the mixed strategy, and we can write it in matrix form as this. and similar is for case for the other one. I have not written it, but we can make the best response diagram for from player 2 perspective also, and we'll get the similar kind of equation, just that B there will be replaced by A and we'll get Y's there. So now comes the main idea of Lemke-Hausen, that we give labels to the points in this polytope. So what labels do we provide to the points in this polytope? As we saw, that points have a mixed strategy attached to it and a value. So if a strategy of player 1, and this is the diagram with respect to player 1. So if a strategy of player 1 occurs with probability 0 in the mixed strategy of that point, then it is added to the label set of that point. Label set we are maintaining, it's a subset of all the strategies of player 1 and player 2. And similarly, not similarly, but for the strategies of player 2, if the strategy of player 2 is best response to that mixed strategy, then it is also added to label set. So we can see in this example. So this point was the probability of heads is 0, i.e. the strategy 1 happens with 0 probability. So this line gets, all the points on this line gets label 1. I am writing it here, but all these points have label 1 attached to them. Similarly, all these points on this line gets label 2 attached to them. And now for these points, the strategy 3, because since the probability of heads is 0, so it is going tails. So player 2 will try to go heads. So choosing heads is the best response, and hence all these points get the label 3 attached to them, and these get label 4 attached to them. And notice that this point has both level 3 and level 4, because both 3 and 4 are best responses to this mixed strategy. If we construct it for the other player perspective also, we will get this diagram, that the probability of going heads for player 2 when it is 0, then that strategy is 3. So this side gets label 3, this side gets label 4, and 2 and 1 are the corresponding labels in this way. Now let's see this. Let's say if we have 2 points, 1 point from diagram 1 and 1 point from diagram 2, such that the combined label, like the union of the label sets, give us all the strategies, then my claim is that that point is a Nash equilibrium. Like the mixed strategy represented by these points are the Nash equilibriums. Let's try to argue this. So suppose from the point 1, some strategies are so for player 1, we have strategies of player 1, and let's say some strategies of them are in label set of this point. That means they occur with probability 0 in this case. So if they belong to the union of both points, then they must belong to the other set. But since they are strategy of player 1, that means that those strategies are best response for this mixed like that mixed Nash equilibrium. Mixed strategy. That means that the point like this point had a mixed strategy for which all of the best response strategies were the ones that had support in like this strategy, and all others were 0. Hence this mixed strategy will also be a best response to this mixed strategy of this point. And similarly we can argue for other direction. Hence both points represent mixed strategy which are best responses to each other, and hence by definition these are Nash equilibriums. So now we have reduced our problem of finding Nash equilibrium to finding such points for which the label may like the union of label sets make the whole complete strategy set. Now we need to find these points, and to find these points, we need a way. Can someone suggest a way to find such points? Okay. So right now, we have few problems with us. We have no known starting point right now. We have no, like, we can start off with random points, but we have no way, like no systematic way to search in these. Secondly, these polyhedrons are unbounded right now, so like they go on till infinity. So now there is a very clever strategy that we can take a projection of these diagrams such that onto unit payoff plane. That means like we want to take some kind of projection so that we like I'll explain this diagram later, but first let's come to this. So we want to take projection of our current diagram such that one, it becomes a closed surface, and then we have a starting point that we can work with. So suppose we had inequalities of these form, that x1 is less x1 plus 2 x3 is less than equal to v. Suppose I divide everything by v, so this side of my inequality becomes 1, and then I work in this coordinate space that my new x is the vector divided by v. Now the points which are far above in this diagram, they get divided by a large v. So it's not like, it's basically taking a projection of this diagram onto the v equals 1 plane, and hence the point at infinity will also get projected. And to what point it will get projected? So if we divide here by infinity, all of this becomes 0. So the point at infinity gets projected down to origin. Observe one thing. Hence it gets squished down into some kind of diagram like this. Like we had this line which had label 1 connected actually with no, I think this one is the correct one. So we have 1 that is connected to 3, then 4, and then 2. And 1 and 2 goes till infinity. So when that point gets projected, both of them gets projected to a point where 1 and 2 gets connected. And hence we get diagrams of these form, that 1 and 2 gets connected. Similarly here 3 and 4 will also get connected. And like you can see here 3 and 4 and we get these diagrams. Observe this, that this point contains all the strategies of this, because everything gets mapped down to 0 probability. Although this is not really a Nash equilibrium point, but it is a point in, these give us 2 points for which if we take the union, we get every strategy in our label sets. And hence this can act as a starting point, even though this is not really a Nash equilibrium, but from here we can start building upon our algorithm. And after this we do something which is pivoting, and that will be now presented by Krishna.
Okay, so since we have developed all the preliminary knowledge required and the preliminary settings required to implement the Lemke-Hausen algorithm, we shall move on to a demonstration based on this example. We have these closed polytopes and we have a starting point represented by these points. Now what the Lemke-Hausen algorithm says when we solve it pictorially, it says that we pick up any one label. First we start from the artificially added pair of vertices. Then we pick up any one strategy label to eliminate from the current set of vertices being current set of labels being covered. To do that, we move along the edges of our polytope such that the vertex that we want to eliminate it does not come in the next adjacent vertex that we reach. Moving in this manner, we might encounter that introducing copies of labels that were originally there. We want to eliminate those copies as well. So we move on in a similar fashion along the edges of the polytope to eliminate those copies as well. we need not retrace our paths, because again that will be redundant effort. We need to move forward along new edges. Eventually, if we somehow reach, eventually, and since Nash equilibrium, existence of Nash equilibrium is always guaranteed, we will reach a pair of vertices where we again have all four labels with us, and the label that we eliminated originally reappears in the last move. Let's move on through, let's work this out through an example. This is the starting point. Suppose we choose label 4 to eliminate or to drop. So to eliminate 4, we'll have to move from this to this vertex. So we move like that and we reach this vertex. But can you observe that in this we have introduced 2 here, and 2 is already present here. So there is a copy of 2. We cannot eliminate the copy of 2 from here, because we will have to retrace our path back. So we eliminate the copy of 2 from here, we move upwards. So we reach here. After reaching here, we've introduced a copy of 3. We need to eliminate that copy. We cannot eliminate it from here. So we use this point. We move rightwards. So we reach here. Now you can see we have a copy of 1. So we move on rightwards here to eliminate that copy of 1. And you can see we originally eliminated 4, and we have finally arrived at 4 again. And we have our entire set of labels being covered. So these are the points that represent our Nash equilibrium in this case. Now, if we project it backwards to our best response diagram, we can see that these 2 points correspond to these 2 points. And by symmetry, we know, and if we work out the algebra of the equations, this point is half and this point is half as well. So both the strategies have the probability of half in the mixed strategy Nash equilibrium of this game. Now, this was a pictorial representation. We might as well do an algebraic representation of the same algorithm and see the analogy between the two. Now, we saw, as Pratham explained earlier, we got our closed form polytopes using these inequalities. We need to eliminate these inequalities and convert them to equalities according to the algorithm. For that, we introduce slack variables. These are the slack variable vectors. Slack variables in some sense are dummy variables. These are inequalities. So if we convert them to equalities, if we say that this equals 1, there needs to be something that makes up for the difference between the two. That is why we introduce these variables. These are the slack variable vectors, and there is a constraint that these need to be greater than equal to 0. So finally, we arrive at this situation. The slack variables here can be seen to be S3, S4, R1, R2. X variable represents the strategies X1, X2, and the Y vector represents the strategies Y3, Y4. Now, we can write these equations in a row by row fashion. This is the preliminary set of equations that we have. Now, this is the original set of diagram that we had. We saw that we chose 4 to drop. We chose to drop 4. So we choose the original strategy variable as our pivot variable. Now we need to identify the term for that pivot variable which has the maximum coefficient, which the coefficient becomes our pivot numeral, and we multiply the equation, the other equation, with the same numeral to achieve this. Now we subtract as many multiples of the original pivot equation from the other equation to eliminate y4. So we do that. In this case, we can see that a single multiple can easily cancel y4 in the other equation. So we arrive at this set of equations. You can see that this is the operation that we performed pictorially, and we can see that now we've introduced R2. If you look closely, there was no R2 here, and we have introduced R2, which is similar in the sense that we introduce a copy of 2 here. Now we need to eliminate the copy of 2 from this side. Again, we do the same thing. We identify the pivot variable, we identify the pivot numeral, we multiply it here, we do the subtraction, and you can see we finally reach at this point. Now you can see, if you look at it closely, before we subtracted there was no S3 in this equation. But after subtracting, we introduce an S3 here. This is similar to saying that there is a copy of 3. We move back to this equation to eliminate the third label. We do the same thing. And in doing the same thing, now if you look closely here again, there is, here we reached a copy of 1. There was no, just one sec. Yeah, okay. So, I'm sorry. Yeah, so we chose the pivot variable here. We subtracted it. There was no R1 here. And when we did the subtraction, we reached an R1 here, which means adding a copy of 1. We move back here. We do the same operations, and we can see that eventually we will arrive at introducing S4 in the other set of equations, which is again similar to saying adding S4 in our current set of labels. And finally, we have reached our Nash equilibria. Now to calculate the probabilities, But the method here is we reduce all the slack variables to 0 and we calculate the unnormalized values. x1, x2 will come out to be 1 by 4, x1 will come out to be 1 by 4, y3 will come out to be 1 by 4, y4 will come out to be 1 by 4. Now when we normalize these values, that is take the average of each of them, then we get half, half and half and half for all the strategies, which is again exactly the mixed strategy Nash equilibria that we achieved. This is what is being said in this paragraph. Now there is a note of caution here. It was pretty easy to eliminate the slack variables here and set them to 0 because this is a simple game. But when the game start becoming more complex, there can be multiple mixed strategy Nash equilibria. And to calculate as many as we can through the Lemke-Hausen algorithm, we need to do a case-by-case analysis of the final set of equations that we achieve. So this is the beautiful way through which we can calculate mixed strategy Nash equilibria or pure strategy Nash equilibria, which is a special case of mixed strategy Nash equilibria. And this is the Lemke-Hausen algorithm, and this is pretty efficient, and this is one of the best algorithms there is to calculate Nash equilibria, which is a fantastic concept and one of the reasons that the world is stable right now. So yeah, and for further and more detailed analysis of the algorithm that we presented, you can refer to the algorithmic game theory book by Tim Roughgarden. This is the reference that we also took, and we highly encourage you to go through it.
Avatardos is also the author, right?
Yeah.
Yeah.
Avatardos, Bajrani and
Yeah. Thank you very much.
Avatardos, Nippos.
Yeah, the room is open for questions if any.
I have a question. Let's simplify the problem. Let's talk about zero-sum games. Like there are still two.
No,
Yeah,
so
so
zero-sum
Lemke-Hausen
games are-
algorithm works only in non-negative reward scenarios.
Yeah. Generally, matching pennies, the classical formulation, is 1 minus 1.
Right.
We change it here to like showcase Lemke-Hausen algorithm. Lemke-Hausen algorithm requires assumption that the matrix is non-degenerate. There are not strategies which give similar kind of responses. Those matrix A and B, they cannot have the like linearly independent result. And then again, the expected payoffs needs to be positive. And that is not. We can't go by this.
Like, but at the same time, you can just change your payoffs by adding enough big constant, right? We did that, and it didn't change the mixed strategy Nash equilibrium because your payoff would still lie somewhere in the middle of the expected payoffs. So I don't think like you can modify this algorithm to make it work for zero sum games. Any other questions? Yeah.
Can this algorithm be extended to for like solving multiplayer games instead of single?
Yeah. So this algorithm in its current form cannot be extended for more than 2 players. And actually that's a computationally hard problem. So we've not done complexity analysis, but Lemke-Hausen in the worst case is exponential time. And all the known algorithms for computing Nash equilibrium, they are either exponential time, and the polynomial time algorithms are they only find approximate Nash equilibrium. So it's actually a computationally hard problem. Any other questions?
So there in some games called like potential games or something. The most problematic situation that arises is you cannot kind of find all the set of Nash equilibrium.
Yeah.
So and best response dynamics that you discussed.
Yeah.
That usually picks out one unique Nash equilibrium if you let them simulate for a long time. If convergence is assumed. So I mean, and then you just talked about approximate Nash equilibrium.
Yeah.
So does that ever generate a set of equilibria? That linear program will pick out one particular set?
I think it can generate multiple of them, but it is not guaranteed to generate all of them. So if you do linear programming only, you can get multiple Nash equilibrium. Like in a problem that we worked out, we actually found more than one Nash equilibrium through this method. In here there was only one Nash equilibrium, so we found that. But this strategy in general can find multiple Nash equilibrium.
So the linear program which you formulated will have multiple solutions.
Yeah, you can find more than one mixed strategy Nash equilibrium through this method.
Any Nash equilibrium point like will have that kind of property that the label sums will like give you the whole set.
No, I understood that, but I was just concerned whether that Nash equilibrium Like a linear program will like give you a unique solution.
No,
I
it will
believe
give
we-
multiple.
Yeah.
It
But
gives multiple equal, but not all.
But not all.
Yeah,
You cannot be guaranteed to find out.
Actually,
Yeah.
there is a very classic game where there are 3 strategies for one player and 2 strategies for another. In that case, there are multiple mixed strategy Nash equilibria, and if you follow this algorithm, you can arrive at least 2.
Any other questions? Okay.
Thank you very much.
Thank you.
The only question I had was that I saw an announcement, it starts at 10:45. So I came at 10:45, by then it has already started.
We were instructed to start by 10.
Yeah, we
Our
all us
instructed.
No, but I saw that there is one program somebody showed me.
Oh yes, yes. I think we started like 5 minutes early.
10:40 you started? Oh, okay. No, it's alright. I was only here in the office, and then because it is 10:45, I came around it, by then it is already started.
Yeah.
Okay.
This is
It's all-
introduced Nash equilibria in the first 5 minutes.
Yeah, that's what I missed. So I should have been there for that, right? So it's okay. That's all. It's well done. Very well.
Thank you, sir.
A huge thanks to Pratham, Krishna and Udit for showing us the logic behind strategic conflict. Now we change our operating mode, moving it from strategic certainty to smart uncertainty.
And that's how we come up to the next session, probabilistic computation and Bayesian machine learning. This session decodes one of the most fundamental challenges in AI, which is how do you make best decision when data is incomplete or noisy? It's about being confident in your best guess.
It revolves around a mathematical idea that tells you exactly how to change your mind when new evidence appears. You start with an initial belief, gather new data, and then adjust your belief in a precise mathematical way. This allows machine learning models to continuously learn and adapt, quantifying their own confidence in decisions.
Exactly. Let's welcome Shweta, Anmol and Nihal to the stage to explain how this powerful computational thinking works.
Hello everyone, I'm Nihal. Me and my friends Shweta and Anmol, we are here to give a brief overview on the topic Bayesian neural networks and probabilistic computation. So as we know, these days most of the LLMs are pretty good at perception tasks or logical reasoning. Like even if we send them an image, they are pretty good at decoding the image, and even if we send them a voice message, they can even decode those. And when we talk about logical stuff and inferences, suppose we just tell like what's the probability of tomorrow being sunny given it's rainy today and these stuff. So most of the LLMs these days are actually good at it. So what they do is something called Bayesian deep learning, which itself is a combination of two models, which include deep learning models and probabilistic graph models. So these deep learning models are actually good at perception tasks, but they can't do inferences to a good extent and logical stuff. And probabilistic graph models are actually good at inference and logical stuff, but they can't do the other. So what we use is a combination of these both, which is called the Bayesian deep learning. And so when we talk about uncertainties in these things, so in real life examples, there's always a lot of error when, there's always an error when we perform these tasks. And suppose we trained our deep learning model and the probabilistic graph model separately. Each one of them in their outputs would yield some error, and when this is taken as input for the other, it will assume that it's perfectly right, the input is perfectly right, and it will proceed. This will lead to the error being accumulated in each step. So rather what we can do is train these models together such that every time output is passed from one to other, it already accommodates that there's some error in the input which I've received. So as I've told, these PGMs are very good at inference and logical stuff. So let's just look at a small example of those. So these PGMs are essentially graphs, and in these graphs each node represents a random variable, and an edge between two nodes indicates that, suppose here there's an edge between A and B. Here it just indicates that the random variable B is dependent on the random variable A. And B and D, there's no edge between them, which just tells that these both random variables are independent. So let us consider this example. Suppose there are 4 random variables, which are essentially indicated random variables here. One is rain, would it rain today or not, and second is do you wash your car or not. The third is if the ground is wet or not, and the fourth is if you are walking on the ground, would you slip on the ground or not. So probability of rain, ground being wet, slipping, and car washing is, if you just apply the basic base formula, it's probability of raining into probability of you washing your car into probability of washing given into probability of the ground being wet given you've washed your car and it rained, and probability of you slipping given the ground is wet. So and the below image is just a naive base which just tells there's one node and the remaining are dependent on that dependent on the other. So how do these actually do inferences? Suppose you know the initial graph and you want to find out probability of rain occurring today given you've slipped on the ground. It's basically probability of raining and you've slipped on the ground by probability of you slipping on the ground. So when you want the probability of rain and slipping, you essentially just do summation over the other random variables, the values it can take. So you can just find this formula here, you'll be getting this one, and this is done in basically exponential time because each time you have to visit all the states which a random variable can take. If the first one, say here if there are n random variables and each is taking 2 values, so it's basically 2 power n here. This is one of the methods. There are many optimized methods. This is a basic one. So we've seen about the PGMs part. Let us get into our first deep learning model, which is a multi-layer perceptron. I would actually like to use the board for it.
Use that board. That is
That region, there is a small region available.
So multi-layer So MLPs are basically, we'll start with a problem statement initially. Suppose suppose there's a doctor and he's testing for a patient to have cancer or not. Suppose the doctor has done some tests initially and he finds out few parameters, say x1, x2, so on until xn. From his test, he concludes these information, and he needs this network to output a value y, which tells if the person is having cancer or not. This will be 0 if the person is not having cancer, 1 if the person is having cancer, and any number between that is basically the probability of the person having cancer. Bigger problem. The inputs are x1, x2, so on until xn, and the output is a single number y, which just tells if the person is having cancer or not. Any number between 0 to 1 is the probability of the person having cancer. So, yeah, the multi-layer perceptron, this is the initial layer, which we call the input layer. Say there are n nodes here, and this is the input layer, and there are actually, the output layer could also be an m-dimensional vector. Here we just talked of one dimension because our output here is essentially a single number. So output in general is another m-dimensional vector, and between these both, to find the value from this to get the output, it essentially performs a sequence of computations through which, and there are hidden layers here. It could be any dimensional. There are few hidden layers here, and from this, and like each node, I mean, say if you want to find the value here, these are the inputs which are given to you, x1, x2, so on until xn, and you want to find the value at this node, so that eventually you can find these outputs. Okay, so this is what the input layer, hidden layers, and the output layers. Okay, so what are weights, bias, and I'll just give an example of the sigmoid function. So weights are essentially, suppose you want to calculate the value at this node. So this node is connected to all the previous layer nodes, and to find the value at this node, you need to know how much role would each other node in the previous layer be playing. So each node will essentially be having a weight here, and the value at this node is determined by these weights and biases. Biases are just to accommodate the real life values. Suppose you need to carry umbrella when you go out, it's essentially dependent on if it's raining today or not. But nobody would like to carry an umbrella with themselves. So even if you get the probability of raining, you would just like to decrease it so that you don't want to carry an umbrella with yourself. So you add a bias to this thing. And the sigmoid function. Sigmoid function is basically 1 by 1 plus e power minus x. It's just a non-linear transformation here. This function essentially squeezes the entire real line into 0 to 1 range. So, yeah, to calculate the value at each layer, suppose I want to calculate the value at this node, say this is y1. So what we do is we take the weighted summation of the previous layer nodes, which is summation xi into wi, I equals 1 to n, and you add your bias to it. Okay, so the final output which you are resulting is basically a number between 0 to 1, right? So you apply your sigmoid function. You can apply any nonlinear transformation. Here I'm just talking about the sigmoid transformation. So you take this value and apply sigmoid function to this, which will squeeze these values between 0 to 1. And in each layer, the values would be lying between 0 to 1. So you can get the value at this node, and similarly by the edges here you'll be getting the value at this node, and so on. So if you represent these weights as a weight matrix wi, so the value which you'll be getting is weight matrix into previous layer plus the biases in that layer. This gives the value at the next layer. So the question is, how do we actually design these weights? I mean, how do we set these weights and biases so that we get closest answer possible? So while we actually train the data, train the model, we know few states, right? If x1, x2 is a particular input, then the person is sure to have a cancer. So we actually know the values of output, and we even know the values of input. So you need to set these weights such that it will be closest to the value of output as much as possible. So what you do is, the value here is actually a function of all these weights, right? So you just need to find this as a function of the weights, and there are many methods to optimize this. I'll be talking about one method called gradient descent in general. So if we just have a function of parameters, say theta 1, theta 2, so on until theta n, and we need to minimize this function as much as possible, what we start with an initial guess here. Suppose here we start with this point, and we know that gradient at any point will tell you the direction of maximum increase of the function. So what you do is, if you transverse in the direction of negative side of gradient, you will get the direction of its maximum decrease, right? So we essentially, suppose you have an error threshold, like you want the error to be less than some 0.1. So you start with an initial guess and just update your values of parameters such that you'll be minimizing your error function less than the threshold value. And this is how the parameters, in real life example, this is a very complex function of these weights because you're applying a nonlinear transformation in between two. So we do this along with backpropagation. I won't be discussing much about it. It's essentially like you'll be setting the value of the previous layer and then you'll be going to each other layer. Okay, so the next model is convolution neural networks, which are CNNs. Again, we'll start with the problem statement. Suppose there's an image and you want to decode it. Here, like this image represents 3 basically, and you just want to decode if it's 3 and which number does it represent. These things are done well by the CNNs. Yeah. So CNNs are also basically multi-layer perceptrons, except with the fact that there are special layers called convolution layers, which are used to identify patterns and stuff. So when we talk about each convolution layer, okay, so there are things called filters and feature space. So what does a filter do? This method is closely related to how humans actually identify it. Suppose it's a number called 7, the input was 7. So what you know is basically it's a horizontal line and a vertical line following the horizontal line. So even this does in a similar way, it just goes on checking for edges. Like each filter basically represents some edge, say if the image was 8 here, we'll define the black part of the screen to be as 0. I mean, when we convert it into the pixel grid, we'll define the black squares to be 0 and the white squares to be 1. And any number between 0 to 1 is basically the shady part, like how much white it is. So, and the convolution product is basically taking the product at each value, at each, I mean, summation aij into bij, if a and b are the matrices here. So, okay, so the filters and feature space. So each filter is present to represent some pattern. Suppose you want to check for a horizontal line, you just make a filter corresponding to this. Suppose you want to make a 3 cross 3, just put 1s here and 0s here and 0s here. So this would represent a horizontal line and pattern. And what you do is, when you have your initial pixel grid here and you have a filter here, you just pass your filter and make your filter to slide through the entire pixel grid and note down the values here. Again, you'll be using the sigmoid function here. I mean, you can use any nonlinear transformation to fit their values. Here, again, we'll be using sigmoid function. So you essentially, you just slide your filter throughout the entire input and you just find out your filter space here. So when the product is maximum, I mean, when the convolution product is maximum, it just tells you that this part, I mean, if the convolution product is maximum here, it just tells you that this part of the image has this line. I mean, it's most probable to have that pattern. So it's doing the same thing here. It just tells you that this part of the image is likely to have this pattern more. So it will be going on checking. In each convolution layer, there are many filters, and it will go on check for these patterns. And there's something called max pooling. When you have a large grid, basically, you don't need to know the exact location that this edge, which is a horizontal edge, is present at this location in the grid. If you have a rough idea, like there's a horizontal edge lying somewhere between here, it's fine, right? So for these large images, in order to make it memory efficient, we just do max pooling, so we don't need to store the entire n cross n grid here. We just take few values. I mean, you can just take one grid here and find the maximum value here and just store it here, and so on. We can just find the maximum values and store it rather than carrying it in every part. Okay, so Anmol will be continuing.
Yeah. So after this, we'll discuss Bayesian neural network. How is it different from any deterministic model? In deterministic model, the parameters, say weights and biases, have single values, but in Bayesian neural network, they behave as random variables and they follow probabilistic distribution. We do this by assigning a belief, for example, that is called a prior. For example, I may say the weights are centered near 0 and the variance is a hyperparameter. And we train on the data, and this updates our input belief to get a Prostetia distribution. Bayesian deep learning, it is a more broader probabilistic framework. As discussed, it consists of mainly two components, perception component and task specific component. Perception component is a probabilistic deep learning model, say Bayesian neural network, where the input is raw data, for example raw text or image. So what it does, it converts it into low level of dimensionality. So as discussed in CNN, the image would be converted into feature maps. And task specific component, the output of perception component will act as input for this task specific component, and this will handle specific tasks, as in it will calculate the probability, what is the percentage that this image is a cat, 90% that this image is a cat, or what is the probability that the person has a specific disease. And there is one more, hinge variable. This acts like a glue or a hinge between perception component and task specific component. How does these three components interact? One flow is supervised learning, where the information flows from perception component, then to hinge, and then to task. Same example, given the image, it will convert into low level of dimensionality, feature map, it will go to hinge variable, and then it will pass the information to PMG, which is the task component, and will determine the probability of the image being a cat. Another is unsupervised learning.
from task to hinge and then perception component. Here the input would be, for example, raw text, thousands of articles, but they are not labeled. We don't know what is the topic. So what the goal of the model is, it will learn by itself. It will form clusters. For example, test is there, exam is there, so it will form into one cluster. Market, stock, business, it will learn by itself that this is one cluster. So this is unsupervised learning. Now hinge component does not only transfer the information but also transfers the amount of uncertainty. This is determined by the value of variance. So it could be zero variance where there is no uncertainty. It will be said that the image is a cat, no probability. Second is hypervariance. The value of the variance would be constant, which would be manually tuned. So for every data, it will say that the image is 90% cat, the image is 90% dog. The uncertainty won't change. Learnable variance, the uncertainty would be changed depending upon the data and will learn by itself. One example of perception component is RBM, restricted Boltzmann machine. Here the word restricted means that the visible neurons are independent, the hidden neurons are independent to each other. It is an energy-based model and the probability distribution is given by a scalar energy function, which is given by this, where V is a visible neuron, H is the hidden neuron, W is the weight matrix. And A and B are hidden and visible biases respectively. We assume that hidden and visible neurons follow Boltzmann distribution, so the joint probability would be given by this function, where Z is partition function normalizing constant, but this is intrackable. We can't find the exact value of this. Here we assume that the hidden and visible neurons take binary values, 0 and 1. So we'll find the conditional probability, say what is the probability that H is equal to 1 given value of V. So this is given by this sigmoid function. Similarly, given the value of H, we'll find what is the probability that V is equal to 1, which is given by again this sigmoid function. So this allows gift sampling. From V we find H, from H V, and then so on. RBM is a generative model. The model tries to learn the probability of P of V. We say that the model is good if probability of V is high. So we'll try to maximize the probability of V. Likelihood is what is the probability of parameters given V. So we'll maximize P of V. By this we'll find the value of parameters W, A and B. So for an RBM, we model P of V is given by joint probability over the distribution of H. We take log function. Log likelihood is given by this. And we want to maximize this. We differentiate with respect to the weight and we get this. E data is expectation of what the data wants. Given the data, given V, what is the value of H? And E model is given the value of H, what is model predict V. So this contains a lot of noise. And plus this value is intrackable, we can't find it. So we need to find an approximate function that approximates the value of this gradient function. So we use a method called contrastive divergence method, where same thing, given the value of V0, we find H0. Given H0, we find V1. Given V1, we find H1. And the difference between V0, H0 minus V1, for example, if K is equal to 1, V1, H1 multiplied by some learning factor will give delta W. So this is how the model learns the weight values. Similarly, this is how the model learns A and B values as well. One example of task-specific component is probabilistic matrix factorization. This is a recommendation model which is generally used in platforms like Netflix, where the user have some vector. For example, I'm a user in like 10% comedy, 5% thriller, etc., etc. And given the item that the movie in itself is 5% thriller, some percent comedy, etc. etc. So for any item j, the latent vector is given by Vj. For any user, this is given by this. We start with some prior belief. We assume this is Gaussian distribution centered 0 some hyperparameter, and this Gaussian distribution 0 some hyperparameter. Here the predicted rating is given by the dot product of these two vectors, but the exact rating would be the normal distribution with mean this and some hyperparameter Cij. So this is again a generative model, so we want to maximize the probability of this posterior function. By this we maximize the value of the likelihood and the given priors. So we take again the log function. Log of this we find this is the function we get. Again this is the function we get. Given the distribution of prior, we take log, we get this. At last the posterior is given by this function. We want to maximize this. Here this square term is called reconstruction error. We want to minimize this, and these two terms are called L2 regularization term. This prevents the overfitting in the data. Here the weight matrix and the biases for W and V, the latent variables, are found by gradient descent method, which was discussed earlier. This is the squared error and the L2 regularization from the Gaussian parameters. One more example for task-specific component is Bayesian inference network. Here, like in the last example, we assume that the latent variables are dependent on each other by some Gaussian function, but the mean is a linear function. But here we assume that the latent variables, for example x and v1, are in itself input for some Bayesian neural network, and they have a non-linear dependency function with mean and variance given by such and such. For any given a factorization example, here x is the, for example, the feature map we get from the perception model. v1, v2, v3 are latent variables. So probability of v1, v2, v3 given x is given by probability of v1 given x, probability of v2 given x and v1, and probability of v3 given x, v1 and v2. Here the individual conditional probability are in itself a Bayesian neural network. A real life example where BINs are used is smart healthcare, where you have to find the missing information of a patient. For example, V1 represents the EKG signals, V2 is the blood pressure of the patient, V3 is the self-reported fatigue level, and V4 is the actual risk of a patient getting a heart disease. So, in real life also V1, V2, V3 are non-linear functions in itself, but a standard model given V1, V2, V3 will predict V4. But what if one of these informations are missing? So, this is where BIN would be used. Given V1 and V2, as this is a bi-directional model, given any two latent variables, it can find third latent variable. So by V1 and V2, we can find V3, and then we can predict the patient getting, what is the percentage of patient getting us some heart disease. So, I'll hand over to you.
So we just saw how Bayesian neural networks do not give us specific answers. They just give us a probability distribution of what the possible solution to whatever problem we've given could be. This also requires the weights and the parameters in the model itself to not be certain values, but to be random variables whose probability distribution we have to decide. Now, if you want to do that using classical computers, you would have to assign a certain value to each of the weights, calculate the output, and measure that output against the expected output to see how accurate that set of values and for the weights are, and do this many times for all possible combinations of the values that the weights can take. Clearly, this increases exponentially, so doing it on a classical computer would be computationally intensive. This is where probabilistic computing comes in, where it inherently embodies the need to sample multiple states and sample them with a likelihood of that being the optimal solution in the hardware itself. Now it does this using these things known as p-bits. These p-bits, you can think of them as classical bits, but you are converting them into a random variable and you are assigning them a probability distribution. Now as you move on and perform multiple iterations or multiple layers in the Bayesian neural network, you change these probability distribution, but there is an inherent randomness to it which allows it to accommodate noise and other factors. Now, how are classical bits, p-bits and qubits different? You can think of it like this. Your friend is in another room with a coin. A classical bit would be that you give a certain set of operations for them to perform, like flipping, moving, etc. And they perform that, and then you ask them for a reading and they tell you what the coin is showing right now. A probabilistic bit would be something like you tell them a set of operations, but they involve flipping a biased coin. And when you ask for a reading, they tell you what it is. But the thing is, you can't predict what the value could have been because it involves some flipping taking place. And a qubit is something like you ask them for a reading, and after you ask for a reading, they do the flipping and the different things that you have asked them to do. So till you have asked for a reading, it has existed as both possible solutions. Now, how do you implement this in hardware? To do this, you need any natural material that has two stable states and can easily flip between those states on introducing natural phenomena. One of the things that we can use are the MTJs, magnetic tunnel junctions. Now, what these are very small scale magnets, nanomagnets that have two stable states of north-south positions. And these are very temperature sensitive, as in they flip when you change the temperature, and they're also sensitive to external currents and voltages. So that is how you build a PV. You take a nanomagnet and you give it some bias using the current or the voltage, and then you give it some input value, and the transistor or the amplifier gives you the magnetic state converted into a 0 or 1 signal that you can be using. Now, since a p-bit cannot work on its own, it needs a network, and the magnetic states of the other networks also manipulates what the state of a current p-bit is. It is necessary to include a feedback loop. Now, to update a p-bit, this is the mechanism that we are going to use. The measure of the ith bit in the t+1th iteration is a signum function that depends on the input bias and a random part that we are introducing. The randomness is given by the input, the excess current or voltage we are introducing. The input bias depends on the bias of the bit itself and the coupling weights and the measures of the other bits around it. This can also be thought of as the probability that the ith bit will change to 1, given that the neighbors are in the state it is a function of the inverse temperature and the input bias it has been given. Now, if you keep doing this Gibbs sampling over and over again, it eventually reaches an equilibrium and it samples the global distribution, not randomly, but in the probability distribution that you want your solution to be in. Now, to consider the terms in the Gibbs sampling equation, the term Bi represents the tendency of the bit, what it locally wants to be itself. The Wij represents the coupling weights with the other bits. If a bit wants to be aligned with the neighboring bit, the coupling weight would be positive, and if it wants to be disaligned, it would be negative. Now, the beta part over here represents the inverse temperature function. This I'll explain in the next slide when you think of a problem as an energy space and so on. And okay, we talked earlier about how when we do the Gibbs sampling over and over again, we reach a equilibrium. To understand what we mean by equilibrium, you can think of the problem to be modeled as an energy space where the most optimal solutions have the least amount of energy. And if you saw in the previous slide, we introduced the inverse temperature thing. Think of it like this. If the temperature of a system is very low, the system would be less forgiving to higher energy solutions. So beta essentially allows you how much error you are going to allow or randomness you are going to allow. Now, in an equilibrium state, the system is still sampling, the bits are still flipping, but they're flipping with the frequency and in which it is proportional to the probability distribution that you want to come into. Meaning it is going to sample the lower energy points way more frequently than it is going to sample the higher energy points. Using the Gibbs sampling method, we can perform a Monte Carlo Markov chain walk. A Markov chain is just a sequence of events in which the current state only and only depends on the previous state. So it is a memoryless property which also extends itself to the equilibrium condition where a detailed balance is achieved. Now this, we perform a Monte Carlo by calculating the energy at any initial point we have taken, using the Gibbs sampling, choosing the next point to go to, calculating the energy there, and finding the energy difference. Now we take a variable A that represents the probability of accepting that transition, and that is the minimum of 1 n e power minus beta delta E. Now what this says is that if the energy difference is a very greater value and you're transitioning to a lower energy state, you are very likely to accept it. But even in some cases, if you're going to a higher energy state with a very small probability, you can accept it. This helps you explore all possible solutions in order to not get stuck in a local minima. You can see a simulation of the mechanism in Java, which shows that you did explore surrounding states, but once you came to a valley, you concentrate towards the middle. This is just a proof of how the Monte Carlo MCMC walk causes the final frequency of the distribution to be a Boltzmann distribution that is an analogy to the physical particles. We talked about Gibbs sampling. There are some other methods of sampling also. The synchronous sampling is when instead of just updating one bit, you update all of them together. Now usually you would do this if you want to introduce more randomness or explore more farther away states from yourself, but this can cause oscillations that are very big or make you get stuck in cycles. Instead, you can do a slightly different version of it called block or groups, where all of the nodes that are related to each other are updated together. And simulated annealing is just using the inverse temperature function that we discussed about before, and decreases the temperature to slowly converge towards the most optimal solutions. Now, one interesting thing about a probabilistic bits is that if within your computation you require to come back from to perform a calculation that requires you to per se find the value, given a value y, given a value z, find what x and y given and give z. You cannot do that in a classical computer because then there is you would have to give one possible output, and that is not 100% correct. Since a probabilistic computing naturally gives a distribution, it can solve these things. So you can use it to solve more kind of problems than a classical computer would be able to. Now we'll conclude the talk while exploring a simple example of solving the AND logic gate using probabilistic computing. Now we know that any combinatorial logical operation can be written as an energy function. To determine the energy function of a AND gate, we write this. Now we could introduce a new variable A that is equal to xy. We don't directly use the variable z because that would lead to a cubic equation, and binary values have the property that x square is always equal to x, and you would not be able to take use of that. So what you do is you define A is equal to xy, and you are trying to calculate if z is equal to A. The first three terms in this equation force A to be equal to xy, and the last term forces z to be A. And the coefficients here are defined in such a way that you are maximizing the energy component or the penalty component if z is not the correct value. If you solve the equation, here you can see that for the correct values of z, the energies are only 0 and 1, and for the incorrect values of z, the energy values is 2 and 3. Now you can still manipulate the coefficients we have taken in the previous thing to ensure that even the 1 is not there, all of them are 0 and all of them are much higher, but this would suffice for now. And you would put your threshold at the energy band between 0 and 1 and 2 and 3 and converge to the solution you want. Now if this we have done mathematically, if you wanted to do it using p-bits, you would have to define your biases and weights. You simply expand the equation that we have defined before, and then you compare it to the equation and you get the biases and weights. This you again just define by the input signals that you're giving to the system, and over time this converges to the solution that we require. That would be us. Thank you. Oh, okay. Yeah.
The lunch break.
Thank you, Shweta, Anmol, and Nihal for that crucial look on modeling uncertainty.
Now, before we satisfy our own computational need for sustenance, we have a mind-bending session that takes us to the absolute limits of computing. We're talking about physics at the subatomic level.
The next session is on simulation of Markovian quantum systems. In simple terms, since building a large-scale quantum computer is still a huge challenge today, we use our current everyday computers to simulate how these strange and powerful quantum systems behave.
The Markovian part just simplifies the simulation. It means the system doesn't need to remember its whole past. Its next state is based only on its current state.
You know, I once knocked the doors of a quantum system and I couldn't tell if it accepted or not until I opened the door.
No one? There are a few. Well, that's the beauty of superposition. Please welcome Sriraj and Ovik to the stage for this exciting journey to the future of computation.
Hello, good afternoon everybody. Today me, Avik and Sriraj would be presenting on how to simulate an open quantum system using a Markovian approach. So we would be defining a few terms on the way before we discuss the final algorithm which we use to simulate the system. So first of all, why are we taking an open quantum system? So first of all, we have in general quantum systems, and open quantum systems are the ones which we encounter the most in reality, because in real life there is always some interaction with the environment of the system, and these are modeled using open quantum system. So the fundamental mathematics of the open quantum system is that we would be solving a matrix first order ordinary differential equation of the form x dot equals to mx. Now in general cases, generally what we do is that we take x to be a n tuple, x to be an n-dimensional complex vector, and m to be an n cross n complex matrix, and we solve this equation. So if we know what is the matrix form of m, we can know what is the time, how the vector x changes with time. But we have one problem here. In open quantum system, even x is an n cross n complex matrix, so the complexity of the problem increases many times. So now we would try to show how we would be simulating this kind of problem. And basically, so these kind of matrix, these kinds of matrix ordinary differential equations can have a very general form, but we will find that to satisfy the physical arguments, to satisfy the physics of it, it has to be of a very specific form. So at first we will be deriving that form of the generator, or which we will be defining now, and then we will be moving to how we simulate this. And so first of all, we would be describing some basics of quantum mechanics, like what is a wave function, and then we would be discussing about the density matrix formalism, which is at the heart of our simulation. And then we would be deriving how, and then we would be showing you how this density matrix changes with time, and that specific form we want to simulate. So physicists at the start of 20th century found out that classical physics can't describe every physical phenomena, especially at the subatomic and atomic level. We need new kind of physics for this. This is called quantum mechanics. So in quantum mechanics, what we do is that instead of talking in terms of the definite position or velocity or other parameters of a particular particle, what we instead do is that we take a wave function, which is a mathematical function, and we see how the wave function evolves in time. And this wave function encloses all the details about the particle. And wave function itself has no physical significance. The wave function, if the wave function is psi, then mod psi square will give you the probability density of finding a particle in a particular place. So the famous physicist Schrodinger gave an equation which is known as the time dependent Schrodinger equation, which is of the form h psi equals to I h cut dou psi by dou t, to calculate how psi changes with time. Here h is an operator known as the Hamiltonian of the system. So in general, psi is a mathematical function, and in many cases of interest, we will find that psi comes out to be a vector. Psi behaves like a vector in a linear space, and h is the operator acting on it. So in many cases, we will see that an n-dimensional quantum system means that the psi is an n complex tuple, and h will be an n cross n matrix. So what we are doing is essentially some kind of linear algebra. And now we see about the time evolution operator. So now we have introduced a Hamiltonian. Hamiltonian in quantum mechanics, every physically observable variable has an operator, and when that operator acts on the wave function, we get the eigenfunctions and eigenvalues. Those eigenvalues are the things we can measure. So Hamiltonian is the eigenfunction for energy. Now what is time evolution? Suppose I have a wave function at time t naught. After time t, it changes to psi of t. So the operator ut t naught that transforms the wave function at time t naught to the wave function at time t. So now if we put this back into the Schrodinger equation, we get that u will be a particular form like this. U is the exponential of minus I h by h cut, where h, capital H, is the Hamiltonian. So now we will be defining in the following slides what exactly the exponential of a matrix means. And now if we take the Hermitian adjoint of both sides, then we get this. Here is an important point. The matrix H is a Hermitian matrix. So what is a Hermitian matrix? So basically the Hamiltonian think of this in terms of an n cross n complex matrix. We take its transpose and do the complex conjugate of each term. That is the transpose adjoint or H dagger of H. So our matrix H is said to be Hermitian if H is equals to H dagger. So now if we perform the dagger of this U dagger, the Hermitian conjugate, so this will be basically, or adjoint, so this will be basically exponentiation of minus I h dagger by h cut, because H is a Hermitian matrix, so h dagger will be equals to H and U will be an unitary operator. So this unitarity is very important because we see that if U is a valid time evolution operator, then U dagger will also be a valid time evolution operator. And in fact, if U transforms the wave function at time t naught to the wave function at time t, then if you apply U dagger on the wave function at time t, it will give you the wave function back of time t naught. So it is unitary time evolution is reversible in nature, because if we can apply U, we can also apply U dagger to get back the wave function back in time. So now we move on to the density matrix formalism. So density matrix, in density matrix formalism, we distinguish between pure and mixed states. So what is a pure state and what is a mixed state? So suppose we have a qubit, which is the basic of quantum computation. So a qubit can remain in either a 0 state or a 1 state like a classical bit, but it can also remain in any linear combination of these two. For example, 0 plus 1 by root 1 by root 2 into 0 plus 1 by root 2 into 1. This is a linear combination of 0 and 1, and there is 50% probability of finding it in state 0 and 50% probability of finding it in state 1. So suppose we have a qubit and we definitely know in which state it is. Either it is in 0 or it is in 1 or it is in some form alpha 0 plus beta 1, where alpha and where we exactly know the values of alpha and beta. Then this is called a pure state. In this case, we define the density matrix. If the wave function is psi, the density matrix will be the outer product of psi with its corresponding adjoint. So what is this outer product? So we said that psi can be thought as an n-tuple, that means an n-dimensional complex matrix, n-dimensional complex vector. So an n-dimensional complex vector can be written as an n cross 1 column matrix, and so this psi, this ket psi, this is called ket psi. This ket psi is an n cross 1 complex matrix, and the thing here on this side, it will be its corresponding adjoint, which will be defined as we take the transpose of it, that means the column matrix is converted into a row matrix, and we take the complex conjugate of each term, and so we have a column matrix followed by row matrix. So an n cross 1 matrix followed by 1 cross 1 n matrix. So when we multiply them, we get an n cross n matrix. This is called the outer product. So basically, with an outer product, we are creating a new operator. This is called the density matrix operator or the density matrix. So the density matrix will have some basic properties like rho square equals to rho, that means it is idempotent. Rho dagger will be rho, that means it is Hermitian. Or the trace of rho gives you the total probability of the wave function, and because the total probability of 1, so the trace is just 1. And if you compute the expectation value, this will be given by trace of rho into A. So an operator A, if we take an observable A, its corresponding operator is A, so trace of rho A will give you the expectation value. And now we move on to mixed state. So in earlier case, we discussed that a qubit can be in 0 state or 1 state, or it can be in any linear combination of the two. Now suppose we have an ensemble of qubits, we have many qubits, and we don't know which qubit is in which state, but we know the probability with which it is in 0 state or in 1 state or some linear combination of the two. So in that case, so there is, so we can't directly know what is the state of a particular qubit, but we know how to talk in terms of them with probability. So suppose the kth state is given by psi k, and the probability of that is pk. So then the density matrix will be given by this summation of outer product of psi k with the adjoint, complex adjoint, and multiplied by the probability of pk and sum over all k. And so like any probability, sum of pk will be 1, and like the density matrix of pure state, it will also satisfy most of the properties, but one property will be changed, that is it will not be idempotent. So that is how we distinguish pure state from a mixed state. Rho square will not be equals to rho, and if we put this rho into the time evolution of the Schrodinger equation, we get that the time evolution of a density matrix will be given by this equation: I h cut t rho by dt equals to the commutator of h and rho. So what is the commutator of h and rho? This is defined as h rho minus rho h. So now we discuss about what is a system and environment. So system is nothing but the part of the universe that we are interested in, and environment is everything that the system interacts with. So one important point is that the Hamiltonian we have been discussing till now was Hermitian. It conserved probability, but now when we move on to an open quantum system, there is constant interaction with the environment. So there will be exchange of particles, exchange of energies, and we will see that things are not conserved, and when they are not conserved, we need non-Hermitian Hamiltonians, and there lies the problem. How to ultimately calculate and simulate this non-Hermitian Hamiltonian. And so basically, thus S, if S is the system and E is the environment, thus S plus E, the total density matrix, the total system, the density matrix of the total system will be governed by a unitary Schrodinger equation. But if we take only the part of it, that is only the system S, then it will become non-unitary and non-Hermitian. And because it is becoming non-Hermitian, it will also become non-reversible because there is loss or dissipation in the system. And these are some of the basic examples of open quantum system. So for example, qubits and solid state devices, they are open quantum system, or an atom or a molecule interacting with the fields around it or the particles outside it. So open quantum systems are abundant in nature. In fact, these closed quantum systems are just an idealization. So now we discuss how we take a partial trace. So partial trace is a mathematical operation. So you have a total density matrix over the whole system A plus environment B. Now we delete the information about the environment B and only retain the information about the system A. So this is the partial trace operation that gives you the reduced density matrix which contains information only about the system A. So how we do that? We sum over the basis for basis J of B. So the information about B is getting lost. And only the information about A is remaining. So now we move on to the paper that discusses the general form of the generator of the dynamical semigroup of n-level quantum systems. We will be discussing all these terms one by one. So one of the writers of the paper, the Gorini, Kosakowski and Sudarshan, among them Sudarshan was an Indian-American theoretical physicist and he was also connected to IISc because he was a visiting prof here and he was instrumental in establishing the Center for Theoretical Sciences here. And so as we discussed earlier, we discussed about the time evolution operator. So that was an exponential of a matrix. So just as we know the exponential of real number or complex numbers, the exponential of the matrix is defined as by this usual Taylor series. So e to the power x will give you a Taylor series for x a real number, and when A becomes a matrix, we also define in terms of the Taylor series. And in our case, A will be IHT and H has real eigenvalues, so this series will non-trivially converge. So now we define what a semigroup is. So suppose we have a non-empty set S, and with that we have a binary operation. So binary operation means we are taking two elements from the set and we are getting one element of the set. And this binary operation will satisfy the associative property. So this gives you a semigroup. And semigroup is important because we will discuss about how the density matrix will be changing in time. So when we apply a particular matrix on the density matrix, it will give you the new density matrix, and that particular matrix that we are operating on the density matrix is actually a Markovian semigroup, which we discuss now. So a Markovian semigroup is a particular type of semigroup where it is a one parameter semigroup. That means there is one parameter which in physical sense will be time in most of the cases. So A naught will give you the operator that is just now present, which will be 1. So when you are applying it at time 0, you are getting back the same wave function, and the semigroup applied at t2 followed by t1, this will be equals to the semigroup applied for time t1 plus t2. And this is Markovian because the open quantum systems are irreversible in nature. So the state of the density matrix at a particular time t just depends on the state of the density matrix and instantaneous time before that. So in a sense, it resembles the Markov chain where the nth outcome, outcome of the nth experiment depends only on the outcome of the n minus 1th experiment. So these are some of the basic properties of Markovian semigroups. And what is important in our discussion is generator. So suppose I have a density matrix at time t naught, and AT will give you this is not A, this is capital lambda. Capital lambda t applied on rho t naught will give you the density matrix at time t plus t naught. So you are we are changing the density matrix with this Markovian semigroup lambda t. And the derivative of that is given as, we can think the derivative as some operator L acting on the n cross n complex matrix rho t naught and giving you the rate of time change of rho. So that L is here the generator. So L maps from, so L is a map from n cross n complex matrix space to n cross n complex matrix space, that gives you this. So we can equivalently write this as this. So the time derivative of rho will be given as L rho t. So this is precisely the problem we talked about in the first slide, where rho is an n cross n complex matrix and we want to simulate L. When we are able to efficiently simulate L, we are done with the open quantum system. So a particular important example in, so the generator will have a SU Lie algebra structure. So what is that? So SU means special unitary. So SUN is the n cross n complex matrix space where the matrices are unitary and they will be traceless. Since they are traceless, so the dimension is being reduced by 1, n square minus 1. So in next slide we show a particular example. We take n equals to 2 and compute the basis for 2 cross 2 complex matrices which are traceless. So these polymatrices sigma x, sigma y and sigma z give you the basis for the Lie algebra SU2. And now we come to the holy grail of the paper, which says that the generator L will have this particular form. Now we will be describing each term one by one. So L rho will be equals to minus I commutator of H and rho. So commutator of H and rho means H rho minus rho H, and plus, so this part is the Hermitian part and this part is the non-Hermitian part. And in this non-Hermitian part, we see that these terms Aij appear, and Fi and Fj are the basis, for the SUN Lie algebra that we discussed with an example just now. And this is also a commutator. The second one is also a commutator. And this Aij are all of these Aij are complex positive n cross n matrices, each of them, and they will form a bigger matrix called the GKS matrix, named after the authors. So this is the GKS formalism that we were discussing about, and if we are able to simulate Aij, then we will be done with the problem. So how we simulate that will be discussed by Siraj.
So we'll continue with that. So now we come to some basics of quantum computation. So a quantum computer is a computer which uses quantum mechanical phenomena to do computation and does it much faster than classical computers in most cases. And if normal quantum computers are available, our task is mostly unitary matrix simulation, and that would be very easy. But as they are not, we need to do quantum computation on classical computers, like as in quantum mechanics on classical computers, and for that we need efficient simulation algorithms, or what we will focus on this case are universal simulation algorithms, as in a universal set of parameters we'll use. So the first idea in the field was given by Feynman, who said that you could simulate one quantum system with another, and a universal quantum system can perform any arbitrary unitary transformation, but as long as we create quantum circuits in that case, where you only need two kinds of gates. You need single qubit gates and you need only 1 2 qubit gate to simulate anything. But the thing is that we need finiteness of the gate set and universality. I mean, I can just have a very small gate set and simulate anything I want using that gate set. So these are some very famous quantum algorithms which we won't be going into, but we will go through those. So Grover's algorithm is the classical search algorithm, which quantum search algorithm, which takes O of root n steps, compared to the classical search algorithm, which takes O of n steps. Shor's algorithm is the very well-known prime factorization algorithm, which is much faster than any classical algorithm of that case, and there are a bunch of other quantum algorithms in diverse fields. Now, we said that, and even in the previous presentation they went over Markov chains, so we also use the term Markovian to say that as the thing that we describe is a differential equation, you can think of it as like step-by-step integration. The next step only depends on the previous step. That is how we get to the term Markovian. So it is one of the primary approaches, and this is where the most development has been done in the field of open quantum dynamics.
So now we will follow the simulation algorithm from these two papers called Universal Simulation of Markovian Quantum Dynamics, published in 2001, and Universal Simulation of Markovian Open Quantum System, published in 2015. I want to notice that one of the authors of the first paper is Chuang of Nielsen Chuang fame, and that's cool. So to appreciate the simulation procedure better, we introduce some new terms called the Baker-Campbell-Hausdorff lemma and Suzuki-Higher-order integrators. So what is the Baker-Campbell-Hausdorff lemma? So e to the power a plus b, like if a and b were numbers, it was obvious that it would be e to the power a into e to the power b. But as these are matrices, there's always an error, and that is just the first one of the error. This is the computer scientist version of the BCS lemma. The error is of the order of the commutator of a and b, and in most cases this cannot be neglected. What you can do is, you can decrease a and b to smaller sizes. Once you decrease to smaller sizes, as we showed in the exponentiation formula, it's just a Taylor series expansion. So when it's on smaller sizes, suppose I make a by n or something, a by n actually when n tends to infinity commutes with b by n because they are almost approximately 0. So they commute past each other. In that case, if I am able to have a very large number of steps in my simulation, it is almost effectively what I want. So we will use very high amount of R, but we cannot obviously take R to infinity. However, error reduction is possible. And we also need to break up the generator. Now, in normal cases, what we do is we have a matrix and we exponentiate it. But why can't we do it here? Basically, what happens in physical systems is that LKs are very specific. LKs always correspond to some process, and exponentiation of the fundamental processes is much easier, and the processes have minimal coupling. So, if we have to simulate the whole matrix, it would be like multiplying. If you have an n qubit system with total of 2 to the power n states, your matrix has a total of 2 to the power 2n entries. It's very clear that you cannot multiply all of these again and again multiple number of times. Instead, if you break it down in subspaces where this can act, this will be smaller subspaces, and the results are known for the simulation of those, and you can use that. We also showed that there will be cross terms of the form the commutator of Li-Lj. To eliminate those, we will have to ensure that the coupling is minimal, and so we will be able to reduce the error. So that is why we need to decompose the generator. So open quantum system evolved under that generator, where you either have a Hamiltonian part or the dissipative component. You can take the Hamiltonian component mostly to 0 because it's unitary, and you can multiply by unitary matrix, that's fine, but we'll focus on the non-Hermitian part. So as we said, direct exponentiation is infeasible. This is called the Suzuki-Leet order decomposition, as is what we were talking. E to the power t summation over k Lk, you can break it down into steps and then you simulate that. So this enables simulation of complex Markovian dynamics, where you just use smaller semi-group channels and you finally product them out. So we have already seen the form of this equation, the GKS equation, where this matrix, now we actually first decompose my total generator in terms of smaller generators, and for each small generator I write the GKS matrix. Now this e to the power TLK is implemented via whatever unitary channels we have, and finally we want to get rho t, which is done by the continued application of that, and the polynomial that you get, the final time complexity that you get, is polynomial in t 1 by epsilon. Epsilon is the error between this, the operator we have, and the actual operator that would be ideally get, and the number of distinct Lindblad operator, like the k, basically k, number of k's we have, number of LKs. So suppose we have a toy problem, is that we want to simulate quantum Markovian dynamics, say on a single qubit, just on a single qubit. So we want to simulate the generator L and exponentiate it to evolve rho 0 to rho t, right? So we need a way to do it universally. Can there be some universal set from which I can just put parameters in that set and get something generated out which I can then apply? So yeah, why don't we map it to something we can just put values in and simulate? And so the best way of this is have a library of generators from which we can use which we can write the new generator as. So any generator is fixed by its GKS matrix, so it's equivalent to finding known GKS matrices, right? So we can thus relate our generator to one generated from a very restricted GKS matrix. Suppose the GKS matrix normally, if it was an n-dimensional system, a GKS matrix would be n square minus 1 cross n square minus 1 dimensional, because that is the number of generators, and you break it down into fi, fj, so aij goes over, ij go over 1 to n square minus 1. But most cases GKS matrices are actually sparse, as we will see in a practical example. So if you can break it down to restricted GKS matrices, we can actually do this thing, and we claim that being able to simulate a generator from a GKS matrix depending on a single parameter. If you only have a single parameter, it is necessary to simulate all Markovian quantum dynamics on a single qubit. but we only then the simulation algorithm gives us a way to find the parameters that we need to put in to get out from the universal set. So first of all, we define two allowed procedures: linear combination, which is basically a fancy name for the Suzuki Lee order decomposition we found there, and unitary conjugation. We'll see what these are in the corresponding slides. So first we go to the operation assumptions that we can apply the unitary operations and we can apply linear combination, and that is what we are trying to do. So what is linear combination? Linear combination means suppose you have two processes, Markovian processes, you can apply them for small time steps one after the other, however times you want, and the process that creates is basically a generated effect of A plus B. As we see that for exponential matrices, this limit is rigorous. It was when R was large, this was an approximate equality, but when R goes to infinity, this is an exact equality. So generator of a process found by linear combination, like 1 by 1 for small time steps, is basically the sum of the constituent generators. So we now turn to the second procedure, which is I have a Markovian channel epsilon. I want to produce a unitary transform on that. I want to unitarily conjugate it, where the unitary conjugation acting on the density matrix is given by U rho U dagger. See that unitary conjugation preserves all the Markovian semi-good properties, because unitary conjugation is just like similarity transform, which preserves all the properties of a matrix. Now for an n-dimensional system, we see that unitary conjugation of my Markovian channel by a U results in the change of the GKS matrix by another corresponding unitary matrix. So we write this U dagger e to the power a t u, we conjugate the Markovian channel at time t by a unitary operator, and that results in the formation of the new generator. This generator, when we put back in the GKS equation, we find that we have a basis change U dagger f alpha u, and U dagger f alpha u is written in terms of linear combination of the new basis is written in terms of the linear combination of the old basis, basically similar to how we do a basis change in linear algebra. And then we can use the traceless property, so we just take the conjugate and we create the conjugate of that equation and apply it here. And finally we get that when we take the trace of this equation, U dagger is identity, so we get finally this identity, that C alpha gamma, C beta gamma star is delta alpha beta. This is exactly the form of a matrix which is unitary. So basically my C alpha gamma is the unitary matrix. So basically by substituting, we obtain the new GKS matrix, which is basically a matrix which has been again conjugated by another unitary matrix. So once we conjugate our generator with a GKS with a unitary matrix, our GKS matrix also gets conjugated with another GKS matrix. C is not arbitrary but is determined by U. So we will go through some open quantum system processes. One of them is called phase damping. Phase damping is given by this process, where you can see that the non-diagonal components go to 0 with time. So basically there's no information of the phase. You basically have some probability of system in 0 and some probability of system in 1, but there is no effect of the linear combination that we can see here. And this represents loss of phase information, but there is no energy exchange because rho 0 0 and rho 1 1 stay the same. Now amplitude damping basically shifts all, amplitude damping is this process in which all of your system shifts information to one qubit and the other qubit basically decays. So you can see this is given by this process, where if you take t to infinity, you can see that only rho 0 0 survives and everything else goes to rho 0 0 plus rho 1 1 becomes 1 and everything else goes to 0. So this is basically excitation population, which is rho 1 1, which decays, and this is equivalent to relaxing a system to its ground state, as in what happens in that way. This was the corresponding GKS matrix of this one. Then this is the GKS matrix for the phase damping one. You can always compute them, and these are unique. So we now come to one of the main theorems which we are going to discuss. We consider general Markovian quantum dynamics on a single qubit. As we said that it was only necessary and sufficient to be able to use a single parameter set. Here my parameter set is theta, and we are going to show how that happens. So suppose our L being simulated is equivalent to be saying my GKS matrix will be simulated. My GKS matrix can be broken down by using a spectral decomposition into this product, and this is unique. And A is normalized to unit length. By linear combination, it suffices to simulate all A dagger. Basically, if I can break this down, I have to simulate these. I can break this down into smaller components and simulate each rank 1 matrix. So I break one vector into the real part and the imaginary part. And now what I do, I can take a overall phase. I can take a overall phase because when I take the outer product, e to the power minus I psi is producted with e to the power I psi, giving you A dagger basically. And e to the power I psi A gives you AR cos phi plus basically gives you a rotation in a different basis, where you can write down these two parameters, and these two parameters undergo a rotation when you apply a psi phase change. Now I can basically choose an arbitrary psi such that my AR and AI become orthogonal and mod of AR becomes greater than equal to mod of AI. Basically my real part becomes larger than the imaginary part and they become orthogonal. Now without loss of generality, A has a real part, as we said, larger than the imaginary part and two parts are orthogonal. Now we perform a unitary transformation on that operator. Now this is basically GA dagger G transpose, basically GA dagger. What G is real, so it as A has a real part and an imaginary part, it does not mix the two. The G acting on the A real part keeps it real, G acting on the imaginary part keeps it imaginary. What happens is that as these are separate, as there is no intermingling, G can simultaneously rotate AR into a different direction and like different direction is into a different part of the tuple and AI into a different part of the tuple which are independent. So basically you can choose so that G of A is of this form, cos theta I sin theta 0 transpose, thus proving what we wanted to say. But what is the proof of necessity? We said it was necessary and sufficient. We showed the sufficiency part. What is the necessity part? So if suppose any GKS matrix is rank 1, you cannot write it as the sum of other rank 1 matrices. So that is one. It's extreme in the convex form. Convex meaning if A is there, lambda will also be in the set. But that's fine. So now if you scalar multiplication of A by a phase, so as this is just a unitary operator, you can write any e to the power or your operator is e to the power I psi into j. Scalar multiplication of A by a phase commutes with any rotation. And what we show here is that when you multiply g to the power I psi A theta, and when you do this, and we finally can show that this is unique. I mean, you only get theta prime equal to theta by doing this operation and nothing else. So we have seen that a one parameter set of generators is necessary and sufficient to simulate all Markovian quantum dynamics on a qubit. Now the next question is, can I generalize it to n dimensions? This is for a single qubit, so only 2 states. Can I generalize it to n states? So we make a conjecture. We say that generating the n square minus 1 GKS matrix basically can be reduced to generalizing to produce simulating all the vectors, all the vector outer products, and each vector, there are n square minus vectors. Take each vector will have a real part and a complex part of each tuple. There are 2 of n square minus 1 parameters, but 2 are fixed due to their mod being 1, and due to your rotation having n square minus 1 degrees of freedom, you can basically eliminate n square minus 1 degrees of freedom from there. You can minus n square minus 1, and we conjecture that we will only need n square minus 3 parameters to be obtained, and so these n square minus 3 parameter universal set will help me finally get the universal GKS matrix form. So can this be extended easily to high dimensions? And we will mostly use linear combination, unitary conjugation as well, but other processes can possibly be used. So our goal is constructing a universal set so that we can simulate it, and we have already seen that this works. For n equal to 2, this is fine. We now generalize it to higher n. So we conjecture that n square minus 3 parameters will be necessary and sufficient. So this is a recap of what we saw. D rho by dt is L rho, and this is the solution e to the power t minus t naught L rho t naught. We are just finding efficient ways to simulate e to the power t minus t naught times L. So we just say that okay, now we give a very restricted family of A's from which simulation is enough. So we say that it is necessary and sufficient to simulate all Markovian semigroups whose generator is specified by GKS matrix given by this rank 1 matrix, where this decomposition is given, that A is decomposed into a real part and an imaginary part, where the real and imaginary parts are given. See that their sums are d square minus 1, so that their sums correspond to the whole space, but there are also other constraints that the mod of AI, mod of AR and mod of AI over 1, and they are orthogonal, the things that we started with, and they are given by this very restricted form. AIR is only given by the cos of an angle, and so there are d square minus 3 angles, and AIs and ARs are completely parameterized in terms of them. So once it's enough to simulate any one of them, you can use linear combination, unitary conjugation to simulate all such generators. So we'll go through the simulation process step by step. So suppose you have a total operator, you break it down into its Hermitian part and the dissipative part. The dissipative part, you can further write a GKS matrix for that, and GKS matrix you can decompose in terms of rank 1 matrices, and each of the rank 1 matrices will give, when given back into the GKS formalism, some generator, and that generator we want to simulate, right? So now we can now simulate AK dagger, and we use the same notion that we use something from the parameter set that we have, universal parameter set, and we can just take a unitary conjugation of that to get back my original generator, and we can just sum them to get the original result. So one of the notable things is we have to use the Suzuki first order integrator for that, which is basically what we saw there. We have to break it up into parts and we have to do it a number of times, where R being my time step is given by this, L2 is a constant function given by the norm of that, and if R scales as this, where epsilon is the error and M is the number of terms of the decomposition, epsilon is the error between what I want and the what simulation I get, and if R is of this form, we can do it up to an arbitrary accuracy. So note that breaking down of GK's matrix of L into rank 1 matrices is basically breaking down L into LKs. So breaking down GK's matrix into rank 1 matrices is basically decomposing L into smaller LKs. And these LKs are minimally coupled, so the simulation algorithm is efficient. So now we go to a case study, we go to quantum biology. So quantum mechanics plays a role in chemistry and hence must play a role in biology, which is highly neglected because quantum mechanics is associated with efficiency in terms of quantum computation, and that we don't see in many cases. But in some cases, for example, the Fena-Matthews-Olsen complex or the FMO complex, almost every photon that is absorbed is successfully transmitted to the excitation center, reaction center, and that is done through the FMO complex. So FMO complex, will elaborate on that, and here evidence was found for quantum coherent energy transfer in the FMO complex, and then after this biological complex has been the subject of the application of quantum biology and basically a large amount of research in quantum biology. So there have been multiple approaches. The first two are classical approaches. We will focus on the quantum approach that we have been discussing right now. Now we look at it from that approach. So FMO complex basically has 7 chromophores, and you have a single, so there's a ground state in which all of them, you can think of this as 7 stepping stones from going from one point to the other, and these 7 stepping stones, when you step on one of them, that gets excited. So you have 7 excited states and one ground state where nothing is excited. So there are a total of 8 states. You can model this by a 3 qubits, model with 3 qubits. The GKS matrix corresponding is 63 cross 63. Then the thing is that that was small for a 2 cross 2 case. We were able to simulate that and find that it was cos theta sin theta. How are we supposed to simulate such a large GKS matrix? That is the fun of physics. Is basically your GKS matrix only has 28 non-zero entries. So that makes our application of the algorithm pretty easy. The GKS matrix is actually a sparse matrix in this case, and we can follow the same steps we have gone through in the discussion of the simulation algorithm and simulate that dynamics for the FMO complex, which we can use for further studies. Now, what is the scope for application? So for any system which is open quantum in nature, this algorithm can be applied, especially if there are similar non-Hermitian terms in those. And basically, once as physical processes are but limited in terms of the physical sense, you can create a library of such processes which can then be taken and applied to get the evolution of the density matrix from one point to the other, thus basically giving us further insight into physical processes. And as open quantum systems again are everywhere in nature, every quantum system which we see in nature is an open quantum system. So if in most cases we do not apply quantum mechanics to such systems in chemistry and biology, but if such algorithms can be applied and the results can be studied, we might be able to get more such insights into open quantum dynamics. Yeah, these are references.
Maybe go to the first slide.
Yeah.
The original problem. I'm very new to quantum.
Yeah,
so
sure. Yes.
Whatever question I'm going to ask, I'm going to be very clear.
As in the very first slide.
Yeah.
Okay.
I just want to understand the correspondence between the ODE that we see in the real system,
sure.
and then how is that different?
71 slide.
Different in quantum.
Yeah.
Also good that you reduce the slide number from 100 to I don't know what is now. Yeah. Anyway, so in physical interpretation, right? Say in the physics setting, so usually if you have a ODE and x is just a vector, what you usually have is something like, say I want to drop a ball in a parabolic. I can basically track the motion, the velocity, and the position using a ODE.
Yeah.
That is, say, a physical interpretation of the one ODE. What is similar example for
quantum
this
mechanics?
case?
Yeah. So basically, your x you can think of as multiple vectors, right? M. So x dot. Suppose this is like a system of vector equations. So your x dot is a total matrix, and suppose each row of it is a vector. So you are saying how the row of that vector, basically that vector, changes, so that vector also has some non-trivial dependence, the dynamics of it has a non-trivial dependence on the other vectors. So basically think of each vector as signifying a state. So one state, dynamics of one state is influenced by the Hamiltonian whatever we have, depending on the other states. So that is why you need a combination of vectors in each of these. In a quantum system, so if one state we would only depend on one state, basically that's what we do when we diagonalize the equation. Basically only the diagonal components transform. But in this case you have vectors, right? So the one vector does not necessarily depend on that vector, how the vector is multiplied by the matrix, but on the other vectors. That is why you need a system of equations, system of vector equations to solve that.
Right. Okay. Now I will give you an analogy for correspondence from OD, disciple OD to say Markov decision process, and try to help me how this is, what is the Markovian correspondence here, the way you solved it. So for simple OD where x is a vector, what usually happens is are you aware of MDPs? Say there is a Markov chain, for example. Now every state transition is basically you have a matrix that you get based on the action that you do. So the transition is a function of your action, and it only depends on what state you were earlier. That is a correspondence of, say, if I discretize this OD, that is what I get.
Yes.
There.
Yeah, exactly. Yeah.
Right?
Yeah.
Now help me understand, if I discretize this system,
Yeah.
what do I get?
It's the same.
What is the Markovian system there?
It's the same as you said, right? Discretizing that, suppose you are doing this on a time step, you are simulating xn plus
No,
1
there the states itself are those x vectors.
Yeah, so suppose here your each vector is like, suppose your xn is like a vector, and you have multiple such vectors.
Right.
And each such vector, so you are doing x dot and you are writing some coefficient into x, and you are just doing xn plus 1 is multiplied by that. Here each of the vectors are changing by that. So you are just generalizing that to higher dimensions. So you are generalizing a vector to a matrix, a singular to a vector, and all that.
So at each step the whole matrix is the state.
Yeah.
The whole density matrix.
Yeah, the physical interpretation is still not very clear. It's fine.
Any other questions? No. Don't. Okay. I thought that was the first one. Yeah. We're doing this time.
So in our setting that you see MDP, they have a direct correspondence from here to there. So in control theory, so there is an idea of optimum region, and that is basically trying to find the optimal setup quality. So that is basically
Is this the same?
solving that could get me, and then for a very long time I was just looking at the density correspondence. They also dropped the name density, and I wanted to understand what is the significance in them. But it's not very clear, it's just vector to matrix.
Thank you, Sriraj and Abhik, for the amazing talk. And now it's time to refuel our systems with a data-licious lunch.
The lunch break is about an hour. Please be back by 1:45 p.m. Thank you.
One of no, I haven't.
groups of 3 and starting.
Welcome back, everyone. Hope your battery is at 100%. Lunch was the recharge, and now it's time to reboot those neurons for the next segment.
Time to shift from receiving information to applying it. This segment is designed to be interactive, challenging, and a lot fun. And now it's time to put your knowledge to the test. Not with coding or debugging, but with questions that tickle your brain in unexpected ways.
Welcome to Turing Trivia, a quiz where computer science, tech culture, and quirky facts collide. From clever software Easter eggs to legendary figures in computing, this is where curiosity meets challenge.
Please welcome our quiz masters Pratik and Vignesh from the Quiz Club.
Hello everyone, we'll be starting with a quiz. Before we start, we have a set of rules. Each team can have members up to 3, not necessarily 3. The quiz will contain 15 questions for a maximum of 20 points. In between the questions, we have some star mark questions according to the difficulty. They will be used to decide in case of tie breaks if 2 teams score the same points. If 3 or more teams block a hint, so in general, in a quiz, what we have is few people know the answers, and let's say they block it. They don't want other people to answer, so they can just if more people know it, they just block so that I do not give extra hints. But since this is a fairly new audience to quizzing, I think we'll limit this rule so that everybody can try to answer the most number of questions they can. And then the word of the quiz masters shall be final. If there are any problems in the question answers, the word of quiz master will be final.
Supreme Court.
Yeah.
It's decided here.
Okay, let's start. Before we start, write your team name, write your names, and yeah. Also write your mobile numbers in case you win. So we'll have to get to touching.
Give a sheet.
Team name could be one of the names of the 3.
Yeah, so team name you can give a generic like one of your names, or if you can come with a creative name for like we came with Turing Trivia. So. Even one is. Anybody wants a teammate? There's one guy here. If you are 2, you can have a teammate. Jagin. Shiraj, you need a team? Okay. Okay, then we'll start. Here's the first question. In February of this year, HP was asked to produce a modified model of the NV printer to cater to the demands of a certain group of people. This specialized printer had to add support for clamping as well as safety features like flame retardant materials. The crucial feature of the printer, however, had to be its ability to print in multiple orientations 0, 90, 180 and 270 degrees. They finally delivered the product which shipped in April of this year, managed to meet all requirements on this checklist, thereby successfully replacing an older model after 17 years. Where was this printer employed to be used? Like, which organization asked for this special set of features in them? Focus on the special, like for hints, like you can focus on the line that features like printing in multiple orientations, flame retardant materials, and a support for clamping. Think of where would this be employed, where would this be used?
Is it like a company or something?
More like an entity where this would be. Let's say CSA in IISc, or maybe something like that. As a hint, I'll say think out of the box. Okay, moving to the next question. In the field of biochemistry, X's law is the observation that drug discovery is becoming slower and more expensive over time, despite improvements in technology such as biotechnology, combinatorial chemistry, and computational drug design, a trend first observed in the 1980s. In economic terms, the law has been stated as being that the cost of developing a new drug roughly doubles every 9 years. The law is named after a similar observation made in an altogether different field. However, it makes one alteration. It reverses the letters in the name of the original law. What is X and what was the original law, that is the reversal of letters? This is a fairly easy question. Like, think of why this should be in the quiz in a database event. Yeah, that's fine. One block's there. For you guys to arrive at the question, you should start from that the law is named after a similar observation made in an altogether different field. Also think, why would you reverse the letters? That should it should make sense. Okay, we'll move to the third question. A recently concluded study rated Chile in the top 5 countries in the world for startups. It found that the country invests the second highest amount amongst all countries of the world in its domestic entrepreneurial community. The government invests $15 million per year compared to the UK's $9.9 million. The study also named Startup Chile, the Chilean government's Startup Accelerator program, as the third most active amongst all such programs in the world. It is wholly publicly funded and is estimated that the startups it has supported have a total value of $1.3 billion. So great is the perceived success of the Startup Chile globally that Santiago, Chile's capital, is often compared to its American counterpart location, earning itself the nickname Y. So there's an American counterpart for this city, Santiago. It's called something like, let's say, X. Based on that, this city has been named Y. So you have to come up with a pun on the original name of the counterpart city in America. Think of which.
For the counterpart city, is it a counterpart because of similar sounding name or just for these?
The similar sounding is like context, like the thing which is happening in San Diego, which is happening in Chile, like the whole thing which is described here. So counterpart of that in America.
If we have X, then what do you get to try?
Make a pun on it, like try changing different things, make it sound like something, and using the context present here.
So why is the nickname of Chile like Santiago?
Yeah, why is Santiago? It's a funny pun. Does the nickname contain?
Food items.
I cannot answer that. Okay, we'll move to the next question. Question number 4. This is a Starmark question. A prominent figure X from the field of literature was a well-known playboy who repeatedly earned the wrath of his wife. Their marriage lasted only a few weeks after the birth of their child Y. X's wife, a brilliant mathematician in her own right, was the subject of a metaphorical dig in one of X's seminal works, where he defends his womanizing habits and calls her too mechanical, describing her as, in short, a walking calculator. Y was raised by the mother, who nurtured them in her own areas of expertise in mathematics and science, while Y never met their father, who died when the child was 8. Y would go on to study mechanical engineering, invent machines, and make groundbreaking contributions, earning a legendary status in the world of computer science. ID X and Y. X is the father, Y is the daughter. Both are very famous in their own field. Y being the relevant connect to the computer science. Y is the female, yeah, daughter. Timeline. She invented machines. She invented, like, so you can get the timeline. It was quite early. And she got a very legendary status in the world of computer science. So some first, just think. X is from the field of literature, so make a guess on that. Both X and Y for 1 points each. Okay, question number 5 now. This is an image. Look what's there and give me context. Like, why is it present in this place? Yes. I'll try zooming. It's not happening. Okay. I'm actually busy right now. Can you talk to me after half an hour? Okay. So I'll just read. That's a moth. This is written moth in relay. Panel F, moth in relay. This is a moth.
You have given the hint.
Yeah, I have given the hint. You can read it says above that started multi-adder test, relay 70 panel F, moth in relay. So that's enough. Okay, moving to next question. I think easiest of this round. Whose 100th birthday was commemorated by Google with this doodle? It was in 2012, if I recall correctly. Just straightforward answer. Whose 100th birthday was commemorated by Google with this doodle?
Was that person alive at that time?
No. I'll answer. Yeah, okay, one block.
Is block available?
You're only blocking, it's fine. Leave the block. Okay. Yeah, it's pretty straightforward question. Just write whatever the first name comes to mind. Moving to the next question. Comcastify is a JavaScript library developed by X. Like all of their other content, the library is for purely comical purposes. The reason behind creating Comcastify, according to the creators, is that images nowadays dash to damn dash. The description goes on to read, with all this internet going around, sometimes you just want to experience the thrill of a dash page dash. The name of the library is an explanation of the effect it produces, referencing the times when Comcast was the only internet provider available. The library therefore offers the ability, purely for kicks of course, to take your modern website back to that era. What does comcustify.js do? Who is the creator? Huh? Yeah, so tell me what X is.
Do you want a person or a company?
Not a person. You what? Yeah, you are guessing the creator, and what does it exactly do? Creator is a like company only. Company.
Can you give some hint?
For the X, the name I think for the X like. Let's start from that. What does comcustify.js do? To answer that, think like since they were the earliest providers, like what used to happen back then that does not happen now, and something related to do with pages, web pages. That used to happen when there was early internet era. Also, it's only for comical purposes, so think on that lines. Okay, next question. From here, Vignesh will continue.
Alright. One morning I was shopping in Amsterdam with my young fiancée, and tired we sat down on the cafe terrace to drink a cup of coffee, and I was just thinking about whether I could do this. As I said, it was a 20-minute short invention. In fact, it was published in 1959, 3 years later. I designed it without pencil and paper. I learned later that one of the advantages of designing without pencil and paper is that you are almost forced to avoid all avoidable complexities. Eventually, the algorithm became, to my greatest amazement, one of the cornerstones of my fame. Set the person X. In an interview with Philip L. Frana, Communications of ACM 2001, identify the person X and tell us what he is describing. Okay, so one hint I can give is he is like. Oh. Fine.
Think of
Alright, next question. The real origin of the term X used today in the technological domain comes from a 1970 television comedy series, Monty Python's Flying Circus. The sketch is set in a cafe where nearly every item on the menu includes X. X is a canned meat. As the waitress recites the X-filled menu, a chorus of Viking patrons Drown all the conversations with a song repeating the word X. Wonderful X. Hence, Xing, the dialogue. The amount of mentioned references of X was made to realize the importance of it and other imported canned meat products in the United Kingdom after World War II, as the country struggled to rebuild its agricultural base. This is the original term of which very famous internet term? Alright, I'll move to the next question. This is related to online and gaming culture. Whenever a new breakthrough has made either in computing power or in the size of computers or embedded systems, the gamer community has always asked the following. Alright. The founders of this were working on a consulting project for the CIA. The code name for this project was X. The CIA saw this as the system to give answers to all questions or some such. The project was designed to use the newly written SQL database language from IBM. The project was eventually terminated, but they decided to finish what they started and bring it to the world. They kept the name X and created the RDBMS engine. Later they changed the name of their company, Relational Technology Incorporated, to the name of this product, which is their flagship product. Identify X.
Block.
In 1989, Tim Berners invented the World Wide Web while working at an organization X. The first website had the URL http://info.x.ch in all small letters. What is X? Whoever said block, could you raise your hands? Fine. This incredibly popular social media chatbot X was modeled after a character Y from an extremely successful science fiction series. This series is well renowned for its eccentric escapades and futuristic themes. The character Y and the chatbot X both have blue skin, are robots, and are programmed to carry out the orders and wishes of their masters. X is formed after substituting the second portion of Y with a number. The name X is a pun on the name. Identify X and Y. I'll just explain this a bit. We have Y. Y is a character from a science fiction series, and based on that, someone has created a chatbot X. You need to identify both of them. And this series is a science fiction series. It is one of very iconic characters it has is a mad scientist. You can get In the early 90s, James Gosling was working with a team on building a new programming language to tackle the problem of platform independence. He first named this language X, inspired from something that he saw outside his office window. Then the name was X changed to Y due to trademark issues with another organization that had a similar name. This language later came to be known for its own virtual machine that its code runs on, making the code written in this language platform independent. It is also hated by beginner programmers due to its verbose syntax. Identify both X and Y. I can't say that. It's tough to give a hint for this. Okay, so why?
How did we get to X?
You have to know this fact. Okay, so why just it's
for X, for X, for X, print for X. Can
no,
we see it outside, right?
Yeah.
Can we see it outside, right?
Not really here.
Okay.
Maybe in the place this was being done, you would have seen.
You can sort of see, but again you cannot see the exact thing. You cannot see the exact same thing that he saw, but a similar thing. If you see outside. Alright, we'll move on. Leonardo was a mathematician who, in this most famous work, introduced the concept of Hindu-Arabic numerals, which he called the modus Indorum, to Western civilization. The name that he is popularly known by today was given to him at the earliest by a notary of the Holy Roman Empire in 1506. Leonardo was called Filius Dash, meaning son of Dash. You have to name what we know Leonardo as today and what book did he write.
No, so
So, the name Leonardo was called this thing, that was the name given to him by the military, or?
No, so the Leonardo was called Furious something dash, and that got amended to a like one title, you can say title, which is the way we know him as.
We just need to give that.
Yeah, you just need to give me his title and his most famous book. Yeah, he was an Italian. Yeah, he's for a hint. Yeah, so he's known for numbers, like something very. Book name, you'll have to know that. I mean, we have kept some questions like these so that they can be differentiated.
Okay, so for the person not. Okay, fine.
Yeah, so we'll collect the sheets and we'll just run through once back so that your numbering is correct. Then we'll collect the sheets in 30 seconds. Okay, the first question is where was this printer to be used? Next question, what is X and what is the reversal of letters? So what laws, like two opposite laws? What is this Y city, sobriquet, which is given to Santiago? ID both X and Y, X from field of literature and Y from field of computer science, both very famous. I think British. Yeah. Give context. Whose 100th birthday was commemorated by Google with this doodle? What does COM-Costify.js do and who is the creator? Identify this person X or tell us what is he describing. Origin of which very famous internet term? Easy. But can it run X? What is X? Which project that led to being their name today? Very famous company, very much in news. Where was the web born? Identify the character and the social media chatbot. Identify the original name and the name we know it as today. Very widely used programming. What name do we know Leonardo as today and what book did he write? Okay, we'll collect the sheets now. We'll discuss the answers right now and we'll announce the winners at the prize ceremony. Yeah, that's after this. Okay, submit sheets. Yeah, please write at least one name from your team and a mobile number.
That was a great round of Turing trivia. Well done to everyone who participated. The winners would be announced after the event. A special thanks to our quiz masters. Okay. The answers will be announced in 2 minutes. Right now.
Take 2 minutes. Okay, let's discuss the answers. Anybody who knows, just raise your hands at them. Everybody submitted their sheets? Okay, what was the answer of this? Yeah, it's the International Space Station. Okay, next question. Moore's law and? Yeah, this is Irwin's law, and the reversal of letter is Moore's law. What is this?
San Francisco.
No.
San Francisco.
No.
Chile.
No. Somebody said this right now. From behind, any guesses? Yeah, it is Silicon Valley. Okay, next question. X and Y. Yeah, this is Lord Byron and Ada Lovelace. Next. Yeah. Yeah, this is the first actual case of bug being found. This was a physical bug, and that's how debugging came in. Yeah, this is Alan Turing. Easy. Any guesses? No, not
The
GitHub.
page loads slowly.
Yeah, that's one part. Anyone for the creator? Not Shreyansh Priyadarshi. Okay, we'll move to the answer. Slow down page loads and the onion. The onion being peeled, it's you could have guessed. And the blanks were load 2 times fast thrill of a slow page load. Okay, easy. Yeah, this is Dijkstra's algorithm. Dijkstra's. Easy. Answers? Yeah, just spam. Doom. We'll go with Doom in this. Yeah, this is Oracle. We can discuss any problems at the end of the quiz. Yeah, this is CERN. CERN where the web was one. Yeah, this is Me 6 and Me 6. So Me 6 and Me 6 from Rick and Morty. So we'll need the exact wording for the both. It's a bot.
It's a model. It's a bot.
It's fine. Java is correct. Oak and Java. Oak, the language is Java. It's a tree we were talking about just outside. Fibonacci and it's Libolabaki. That's it. Yeah, this is the Fibonacci numbers we referenced. Okay, thank you everyone. We'll announce the winners at the end. Okay, thank you.
Excuse me guys, where are you going? Please be seated. We have a lineup of student talks. Right? You did not come only for the quiz. Please be seated. There is no going anywhere. The doors will be closed.
Any discussions regarding the quiz shall take place after the whole event is over. No, you. We request the quiz masters to come back on stage for felicitation, and we request Pragnay for it. People kindly settle down. Next, we reboot into game theory with impartial games, a pure simplified class where the rules stay constant for all players.
The talk focuses on the powerful Sprague-Grundy theorem. Imagine being able to look at any of these games and know how sure you are to win. This theorem gives us a mathematical tool for 99.9% win rate.
It works by reducing the entire game position into a single essential number. It's a pure, elegant piece of mathematical logic that simplifies complexity down to a simple value. It's vital for competitive programming and AI game design.
Oh yeah, one last riddle to set the mood. I have no memory of the past. I care not who takes the pieces. And I simplify complexity down to a single value. What game am I in?
That sounds like the ultimate simplification tool for games. It must be the Sprague-Grundy theorem.
Precisely. Let's welcome Shankhadeep and Himanshi to the stage to decode this brilliant piece of mathematical logic for us.
Okay, hello. So let me start this with a question. How have any of you guys heard about the NIM game? So, okay. So for those of you who haven't, NIM game is a two-player game with alternating turns. You will be given n piles and each having some stones. At any particular move, you can select any number of stones from whichever pile you want. And the player who makes the last move wins. That is, if you cannot make a move, you lose. So, we would like to call a volunteer who would like, does any of you want to be a volunteer? Sure. Okay, so would you like to play as a first player or second player?
I don't know, I'm not solved the game yet.
No, any
Just
choose any.
Okay, so
Choose your move.
choose your move. You can select any number of stones you want from a particular pile only in one move.
Okay.
So, just click.
Tell me how many? Two. The opponent has played.
Opponent has played. Now again, you can select any number of apples you want.
Let's see where the game goes.
So in the initial state, there were 11, 4 and 15 apples in the game. And let's see if he can win.
Wait. What is the rules again? Check, choose any pile and remove any number of apples.
Choose any pile and remove any number of stones you want.
If you can't play a move, you will lose.
Okay.
So can the audience see where the game is going?
Yeah. So.
Okay, so this is a loss for him. So would you like to try again? Maybe one more try.
Okay.
Okay. Okay. Anyone else? Okay, just come. So
You can choose any number of apples you want from a particular pile at a particular moment. Just
try to repeat. Just take. Any move.
Okay, so can you guys figure out at this point, will he win or lose? Yes.
Okay, so you can see the game is over. So okay, you can.
Yep. Okay, so can you guys come up with a strategy to play this game? So, well, it turns out that in the previous game which we saw, whatever move you play as a first player, you cannot win this game. This, now how do we come up with a winning strategy? Here is where Sprague-Grundy theorem comes into picture. And NIM, okay. So NIM and many other games are classified into something called impartial games. So what are impartial games? They have finite number of possible game states. It is played between two players only with alternating turns. Game cannot end in a draw. Set of possible moves at any particular move is same for both the players. And the last player making a move wins. So as you can see, NIM satisfied all of these properties, hence it is an impartial game. Now if we take an example of chess, can you guys see why it is not an impartial game? So because the set of possible moves at any particular move is not the same for both players. The person playing with black pieces can only play with the black pieces, and the person playing with white can only play with the white ones. Let's look at one more example of an impartial game. Consider a chessboard. Now each cell of this chessboard contains some knights. Each knight, at any particular move, you can take one knight and you can move it as shown in any of the four moves shown by red arrows in the figure. And you take alternating turns since it is a two-player game. And the player who cannot make a move loses. So as you can, we'll simplify this game within a couple of slides. Now let's look at some more properties of impartial games. So any impartial game can be thought of being played on a directed acyclic graph where vertices are game states and edges are the possible moves. So as you can see this diagram, this is a NIM game where you have two piles and you have one stone in each pile. So 1, 1 represents the number of stones And this is the initial state of the game. In the first move, you can either remove a stone from the first pile or you can remove a stone from second pile. So these two vertices show the next move, like the first move which you can make. And after that, you have only one possible game state remaining. You remove the one stone which was whichever pile it was in, and then you reach 0, 0. So this is a directed acyclic graph, and it NIM is being represented on this. Now let's look at a NIM game with 2 piles. The 1, 1 was quite a trivial example. You have 2 piles. You have one pile with 3 stones and the other pile with 5 stones. Now, as a first player, can you think of a strategy to win this game? So before that, okay, so every state in an impartial game can be either a winning or a losing position. Because the game cannot end in a draw, we can also define it as winning and losing position. Now, a position in which no move can be played or all available moves take the game to winning position for the opponent is a losing position for you. So, for example, if you are given this state and you have to make a move from this, it is a losing position. Because you can just replicate whatever, so after you play a move from the 3, 3 pile, whichever move you play, the opponent will try to copy your move, and at the end you are remaining, suppose, with 1 stone here and 1 stone here, and again the opponent plays the game, and then, you remove the 1 stone and then you lose. So basically this is a losing position for you and winning position for opponent. What we can also observe is if there are 2 piles and both have equal number of stones, it will always be a losing position for you if you are about to play a move after they are equal. Now, a position is winning if there is a move that takes the game to a losing position for the opponent. So, for example, what you are trying to do here is make the 2 piles equal so that the opponent plays a move after the 2 pile contains equal number of stones so that you can win. So when there was a stone in first and 3 stones in second, you remove 2 stones and then you made the position a losing position for the opponent by equalizing the number of stones in both the piles. Okay. But this was an example which we could think of quite easily, but what if there is a very large number of piles instead of 2? Then the number of game states could become exponentially large. So what do we do in this case? Here is when Sprague-Grundy theorem comes into picture. Now Shankar will explain about it.
So feel free to stop me at any point and ask questions if you have me. So now for these kind of impartial games where set of possible moves is same for both players, we saw number of game states can become very large. So Sprague-Grundy theorem in such kind of cases provides us a very powerful method to figure out winning and losing positions for this game and to figure out what move should you play next. So what does Sprague-Grundy theorem say? Sprague-Grundy theorem on a high level it says that any impartial game is equivalent to an n-pile lim game. So what does this mean? We will look at this a couple of slides later. So now how does this work? So what Sprague-Grundy theorem does is there are finite number of game states, and for each game state it associates a number called the Grundy number with each game state. And so before going into how can we calculate Grundy numbers for given states, let's look at some more definitions. So this is the definition of max. So what is a max? Max is basically minimum excluded. So given a set, max is the smallest non-negative integer that doesn't appear in the set. We define this to be max. So if we take some examples, max of the set containing 1, 2, 3, as you can see, this will be 0 because 0 is the smallest non-negative integer that doesn't appear in the set. If we take another example, max of 0, 1, 5, 6, what is the smallest non-negative integer that doesn't appear in the set? It is 2. So max of this set is 2. Is it clear till now? So, and just to make sure you are all on the same page, so this is XOR. So XOR is an operation between binary numbers. For 2 single bits, XOR is defined by this truth table, where if the 2 numbers are same, then XOR is defined to be 0, and if the 2 numbers are different, then XOR is defined to be 1. And for general numbers, for example 26 and 17, how to find the XOR of them? We first convert them into binary numbers, and we take the bitwise XOR of each of the positions. And another property is XOR is an operation which is commutative and associative. So if you have multiple numbers, say 5 to 6 numbers, you can individually, you can take 2 numbers at a time and calculate the XOR and take the final XOR value. So this was the definition of XOR. So now if you remember that for every game state we try to associate a number called the Grundy number, which will contain some information about each game state. Now how are these numbers calculated? So for a given game state R, we will represent the Grundy number as G of R. So for a given game state R, if after one move the possible positions that you can be in are S1, S2 and so on up to Sk. So you are in a given game state R, you play a move and now the game can be in one of these K positions. Then the definition of Grundy number is an inductive definition which is given in terms of the states the bigger game state reduces to, and the definition is given as the Grundy number of this bigger state R will be given in terms of the smaller states which can result after single move, and it is given as the max of the set G of S1, G of S2 and so on up to G of Sk. If this looks complicated, we will take an example. So now let's calculate the Grundy numbers for a one-pile lim game. How will we calculate the Grundy numbers for a one-pile lim game? So now if you see in a one-pile lim game, how can we classify the game states? Any game state in a one-pile lim game can be classified uniquely by the number of stones in that given pile. So we can represent any game state with a specific number n. Now we will calculate the Grundy numbers for this one-pile lim game. We will try to associate a specific number with each state of the game. So suppose the pile that we start with has no stones in it. What is the set of possible moves? You can't play any move. So the set of possible moves is the empty set. So the Grundy number of the state in which there is a single pile containing no stones will be given as the max of the empty set, which is 0, because 0 is the smallest non-negative integer that doesn't appear in this set. Now if initially the pile contains one stone, what are the possible game states? What are the moves that this state can reduce to? There is only one possible move. You can remove one stone and it will result in the pile containing no stones. So Grundy number of this state, again by the definition that we saw earlier, can be given by the max of the smaller states that the game reduces to. Here the smaller state is 0. Max of the set containing the element G of 0. G of 0 is 0. So max of the set containing the only element 0 is 1. Is this clear till now? And let's look at how you calculate for the larger states. So let's take another example. If you have initially two stones in the pile, there are two possible moves. You can either take one stone from the pile, it will result in the pile containing only one stone, or you can take both the stones from the pile. It will result in the pile containing no stones. So from the state 2 we can reach two possible states. So Grundy number of the state 2 will be given as max of the set containing Grundy number 0 and Grundy number 1, because from 2 we can reduce to these two smaller game states. So this will be given as max of 0 and 1 using the Grundy numbers of 0 and 1 that we already calculated earlier. This will be 2 and so on. You can see that the pattern continues, and by induction we can say that Grundy number of the game state n will be n when we are playing a one-pile lim game with n stones. So is it clear till now? Any questions? So now how are these Grundy numbers useful? This was an abstract definition of the Grundy numbers. So what information does it contain? So it is not very intuitive, but it turns out that if the Grundy value of a given state is 0, then it is a losing position, otherwise it is a winning position. So this is not very hard to show, so try to prove this after the talk. You can come up with it. So essentially let's try to get some intuition behind this. What does it mean? Grundy value of a given state is 0, then it is a losing position. Otherwise it is a winning position. We can prove this inductively. And what does it mean for it to be a winning position? There is a move that takes the game to a losing position. And what does it mean for the game to be in a losing position? There is a move that takes this game to a state, but the Grundy value is 0, which is equivalent to saying that there is a move that takes this position to a losing position. So, but if you see, we are calculating the Grundy value for each game state, but number of game states is still exponentially large. So how can we resolve this problem? So there is an easier way for simplifying larger games, which we will see now. So there is an interesting game theoretic result. If we have an n-pile lim game, the game is being played on n piles. At each step you are choosing a particular pile and removing some stones from it. So it turns out that we can think of this game as being played parallelly on n piles. It can be thought of like there are n piles. You are at any step you are choosing one pile, and from that pile you are making the move. You can think of this game as being played on n. You can think of this game as playing n one pile lim games in parallel. So you will choose one pile and you will make a move in that pile. In other words, you will choose one of the n parallel games and you will make a move in that game. So in such kind of cases, if a particular game G can be thought of as games G1, G2, Gk running in parallel, in that case the game G is called the sum of the games G1, G2 and so on up to Gk. There is a formal definition to this which I will not go into now. There is a theoretic definition which exactly defines what is the sum of games G1, G2, Gk. Basically for now you can think of this as there are k games. At each step what are the possible moves? K impartial games. You will choose a game and you will make a move in that game. Second player will choose one of the games and will make a move in that game. And whoever person cannot make a move will lose. So does this make sense, Shrilda? So now in such kind of cases, when a particular game G can be thought of as some combination of some component games, in that case there is an interesting game theoretic result that relates the Grundy value of the game G to the Grundy values of the individual component games. So what is the result? If a particular game G can be described by the set R1, R2, Rk. Now what is R1, R2, Rk? If a game G has the component, if a game G can be thought of as being played parallelly on G1, G2, Gk, Ri is the state of the game Gi. We can think of this set representing the state of the game G uniquely, where the state of the game Gi is represented by the number Ri. In that case, the Grundy value of the composite state in the game G will be given as XOR of the state R1 in the game G1, Grundy value of the state R1 in game G1, Grundy value of the state R2 in game G2, and so on, Grundy value of the state Rk in game Gk. Now how does this result come? The proof of this is beyond the scope of this talk, but there are links attached, you can take a look at this. But we will see how is this useful, how can we apply this to simplify the games. So now we already saw that for a one pile lim game, just a recap, that if a one pile lim game had a pile contained k stones, each game state was represented by the number of stones in that pile, and the Grundy value of the state k, which is basically the one pile containing k stones, was given by the number k. Now let's look at the complicated game. Suppose there are 3 piles with the stones 11, 4 and 15. Now how can we calculate the Grundy value of this composite game? So I already told this 3-pile game can be thought of as playing 3 games in parallel on 3 piles. You will choose one pile and you will make a move in that pile. So in this case, by the special theorem that we saw, the Grundy value of this composite state 11, 4, 15 will be given by XOR of the Grundy value of the state 11 of the 1-pile name game, Grundy value of the state 4 in a 1-pile name game, Grundy value of the state 15 in a 1-pile name game. What are these 11, 4, 15? 11, 4, 15 are the states of the component games. And what are these Grundy values? These are the Grundy values in the 1-pile game. In a 1-pile game, when the 1 pile contains these number of stones. And what is the XOR of them? If you remember, Grundy value of this state, when we consider a 1-pile game, G of k was given by k. So this will be given by XOR of 11, 4, 15. It turns out to be 0. You can do some calculations. So what does this tell? Grundy value of this composite state is 0. And if you remember clearly, this was the starting state of the first game that he played. So this was a losing position. And I had programmed in such a way that computer will always play the best move. So whatever moves he plays, a move will be played that will lead him to a losing position. So from this state you can't win because the Grundy value is 0 if the opponent is smart enough. Now let's take another example. If you have 3 piles with 2, 3 and 4 stones in them, in that case, as we saw already, what will be the Grundy value of this state? It will be XOR of 2, 3, 4, which turns out to be 5. You can do some calculations. So this is a winning state. Now, okay, this is a winning state. Now what move can you play? Can you think about this for some time? What move should you play here? So your task is to convert this into a state with Grundy value 0. Any ideas?
Can you make 2 of them equal?
You can't, because you can only choose 1 pile and remove some stones from them. The other 2 will still be non-equal.
We may try
And what was your main idea behind that?
We'll make the next state as or 0.
Yes. So mainly, the main idea for this was that, main observation for this was that XOR of 1, 2, 3 is 0. What does this mean? For the state in which the 3 piles contain 1 stone, 2 stone and 3 stones, the Grundy value of that state is 0 and hence that state is a losing position. Can you convert this state to a losing state for the opponent? So what you will do is you will remove 3 stones from the last pile and you will make it a losing position for the opponent. Now, so what did we see till now? Till now we saw that if the piles contain A1, A2 and so on up to AN stones, so the result that we derived was, if XOR of the numbers is 0, then it is a losing position. And if the XOR of these numbers, of the number of stones in each pile is non-zero, then it is a winning position. This is what we deduced. That from this state you can always make a move that will make the XOR of the number 0. Okay, so this is how we can apply the theorem. Now we will look at two more examples. So
okay, so this is a slight variation of the NIM game. In NIM game, we had n piles and we could choose any number of stones we wanted from any one of the piles. So here it is also an n pile NIM game. You can choose from one pile only at a particular move, but you can choose only 1, 2 or 3 stones and remove it. So how would you calculate the winning and losing positions for this game? As we saw that n pile game can be converted into n 1 pile games. We'll do the same. We'll analyze a 1 pile game, and remember that we are allowed to only remove 1, 2 or 3 stones. So in a 1 pile game, if the pile was empty, we couldn't make a move. So G of 0 would be max of empty set, which is 0 as we previously discussed. Similarly, for 1, the only move we can make is remove a stone. So G of 0, remove the remaining stone. So G of 1 would be max of G of 0, which is max of 0 which is 1. Similarly, G of 2, would be a mix of g of 0 and g of 1, which is 2. Similarly for 3, g of 3 would be mix of g of 0, g of 1, g of 2, which is 3. Now, if we are given a single pile with 4 stones, what moves we can play is we can remove only 1, 2 or 3 stones, which lead to the state that we are left with 1, 2 or 3 stones. So g of 4 is mix of g0, g1, g2, g3, which is mix of 1, 2, 3 is equal to 0. So we see that if a pile has 4 stones, then it is a losing position. Basically, you will just remove the 3 stones and then like you can trivially see that it will lead to a losing position. Now for 5, again you'll removing 1, 2 or 3 stones leads to these states G2, G3 and G4, which is mix of 2, 3, 0, which is 1. Now by induction we can see that G of k is k mod 4. We can see that this pattern repeats and the pattern is given by this. Now, let's come back to the original game we had. We had n piles. So, suppose we had a1, a2, an stones in those n piles. Then the Grundy value of the state would be, by the Sprague-Grundy theorem, it would be given by XOR of g of a1, g of a2, g of an. Now, since we already calculated in the previous slide that g of k is equal to k mod 4, we already have the values of all the individual GAIs. So we can easily calculate the value of the Grundy value of each of the GAIs, and thus we can figure out if the position is a winning or losing position at any game state, at any given game state. So this was the problem. Now,
so let's go back to the first example. So what was the example? We have a chessboard and each shell contains some knights. There can be some shells which don't contain a knight. And each knight is allowed to make one of these 4 moves. What are these 4 moves? Basically, if you play chess, then you will know that any knight has 8 possible moves, but we are restricting the moves to only these 4 moves. Basically, in high level, the knight can only move left or top. Basically, you can play the moves shown by arrows in this figure. How does the game go? There are 2 players. At one point, a player chooses a knight and makes one of the 4 moves. And what is the condition? That you cannot play a move out of the board. And whoever cannot make a move loses. Now can you try to simplify this game? Can you tell me how can you simplify this game? Using the ideas that we saw. Any ideas? How can you simplify this game? There are a lot of knights. Knights can be placed anywhere randomly. Any ideas? No, I mean, how you try to simplify this game with the ideas that you saw till now.
We can consider them as the sum of individual knights.
Yes. So if you see, if there are k knights, at each move what is happening? A player will choose one knight and will play a move with that knight. Essentially, you can see is what you can think of this game considering being played with each knight in parallel. Basically, you are choosing one knight in each move and you are moving that knight. So we can consider this game as some of the games where there is only one knight on the board. So you can break the whole game where there are a lot of configuration can be very complicated. Anywhere the knights can be randomly present. So we can simplify this game into a game where there is only one knight. Yes.
But if there is already a knight in a position, can I put another knight on top
Yes.
of that?
So now you can see that we can simplify this game into a game where there is only one knight. And then how can we calculate the Grundy value of the composite game? We already saw. Now if we have the game where there is only one knight present, can you tell me how can you characterize, how can you properly define the Grundy values? Yes.
You could break them into the x and y axis, and then you can break the knight into 2 piles, and for each pile you could remove 1 or 2 stones or add 1 or 2.
Okay. That is a good idea. Any more ideas? Any more ideas?
I was just saying that since you will said going to top and left, so in that case we'll just see the maximum number of moves the knight can make till it reaches the end of the chessboard, and that would be the vertical impact.
Is it so? I mean, it is hard to see, but you can try to think in that lines. But I will give you a simpler way to think about this. So first, try to characterize the game state. What is the game state here? If there is a chessboard containing only one knight, what is the what immediately represents the game state? Yes, the coordinate of the knight in which the knight is currently present uniquely represent the state of the game. Now, so you can see that the coordinates here are the game states, and for each game state you can calculate the Grundy values. So basically what we will do is you will associate a Grundy number with each shell of this chessboard. You will associate a Grundy number with each shell of this chessboard, which represents the Grundy value of the state in which the knight will be present on that specific cell. And then how can you simplify that composite game? If there are k knights present in the coordinates, if there are k knights present in the coordinates x1, y1, x2, y2 and so on up to xk, yk, and how will the Grundy value of the composite state be calculated? Grundy value of the composite state will be given as, again, XOR of the Grundy values of the individual shells, which you already calculated. Now I will just give you a way how to basically figure out the Grundy value of each shell. You can see from the top leftmost shell, you cannot make any move, right? So from the top leftmost shell, what is the set of possible moves? Empty set. Max of that is 0. For the topmost shell, Grundy value is 0. Take the shell 2, 1. From that shell also you cannot play any move. Again, Grundy value 0. Take the shell 1, 2. Can you play any move? Grundy value of the shell is 0. Take the shell 3, 1. Is there any possible move? Yes, you can play one move. From 3, 1, just take some time to digest this. From 3, 1, you can move to 1, 2. There is only one possible move from the shell 3, 1. And Grundy value of that shell 1, 2 is 0. So Grundy value of the shell 3, 1 will be given as the max of the set 0, containing only 0, which will be 1, and so on. You can basically see in a diagonal fashion we can calculate the Grundy value associated with each shell. So, and how will you figure out the Grundy value of the composite state? If the coordinates of the knights are given as x1, y1, x2, y2 and so on xk, yk, Grundy value of the composite shell will be given as the XOR of the Grundy values of the individual shells. So you see the power of the Grundy theorem. How did it simplify the seemingly complicated looking impossible kind of game into this simple configuration? So now looking at any position, we can tell if it is a winning position or losing position. Now here comes one thing. We saw that we can now very quickly identify if a position is in a game is winning or losing. But we did not discuss that if a position is winning, what move to play. So since we have less time, I will leave it as a food for thought for you. So try to figure out that how can you, from a winning position, what move should you play to make the opponent come to a losing position. This can be done in O of n, where n is the number of piles. Just try to figure it out. And we saw that sometimes figuring out a pattern in the Grundy numbers can simplify the game quite a lot, but there are still open problems where a pattern in the Grundy numbers are still not known. You can explore this.
So these were the references that we used for learning Sprague-Grundy theorem. And thank you. Hope you enjoyed the talk and we were able to instill some curiosity about combinatorial game theory in you. Okay, question.
Any questions?
So in the Knights game which you just illustrated, so there we are assuming that all of the kind of games are going in parallel, because you said that one square there might be more than one line. So what if we add add an interaction between the knights in that case? Like say that if a knight is present in one square, the knight cannot move something of that sort.
You can think about it. It will most likely not be an impartial game, but you can try to think about it.
Sure.
Any other questions? Any questions? Thank you.
Thank you.
Thank you, Shankadeep and Himanshi, for showing us the elegance of impartial games.
Snack overflow detected. Time to munch. The snack break will last until 4 p.m.
Yes. Is it open? Did you check whether it is open?
No. Welcome back everyone. Kindly settle down.
The next the next The next talk is about algorithms versus luck. It's a clash you didn't know you needed. This session dives into the algorithmic analysis of gambling strategies.
This is not about promoting risk, it's about risk management and computational strategy. Algorithms are used to calculate the precise odds and the expected value of every possible decision. They ignore human emotion and simply calculate the move that maximizes success over the long run.
It's a perfect case study in optimization. It shows how the abstract tools you learn like probability, simulation and statistical modeling can be deployed to understand and even minimize the risk in real-world systems built on chance.
Ooh, I have a good one. Why did the programmer quit gambling?
Why?
Because he ran out of tokens and realized the house edge was an unoptimized variable.
Exactly. Please welcome Prince and Shubham to the stage to analyze the logic behind high-stakes decision making.
One minute. Hello, hello. 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 Hello.
ये क्या
Hello everyone, I'm Prince and this is Shubham, and today we will see how we can intersect psychology and mathematics in gambling, how a gambler loses and how these losses accumulates into machine learning and finance. So we'll start with psychology and let me see how we'll end up in finance and machine learning. Yeah. So why do people gamble, even despite losing odds? I mean, everyone knows, right? The house always wins. Even the expected utility theory predicts that no one should gamble, but humans do, millions of them. Well, we will need a more of a psychological and a mathematical model to see what's really happening here. So, studies show that people maximize expected satisfaction, not money. This is where the utility function comes in. Utility function is a function with the satisfaction and your wealth. It basically, as you can see in the diagram, it's concave, which means it's risk averse, meaning you would rather not lose money than gain more. For example, if I say, would you rather have 500 rupees right now, or if you would rather have 500 rupees right now, or I could give you 1000, but only with the probability of 1 by 2. So most people would prefer to have 500 rupees, despite having same expectation, because, well, it's not risky, right? You're getting 500 rupees with the absolute probability, while if you go with the risk, you might end up with nothing. Hello. Yeah. So even for a fair game, as you can see in the equation, this equation is less than u of w naught, meaning rational agents should not gamble, but humans do it anyway.
To even improve the expectation utility theory, scientists developed a new theory, cumulative prospective theory. It doesn't in this the decisions are not made only by the total wealth. It is made by the change in wealth. That is the like dynamic wealth. You can see here the V is the prospect value, which is analogous to the expectation value, and pi I and Vx are basically these functions where Vx is the probability that humans perceive, like it is the value function of a probability. As you can see, it is not symmetric in x and y axes. And Wp is the weighted probability, which means humans sometimes don't like take the objective probabilities same as the subjective probabilities. And the difference of that is the pi I function, which we use in the calculation of V. And here the graph, as you can see the Vx graph, it is not symmetric in both sides, x and y direction. And the Wp graph would be a S-shaped graph. The parameters we used were alpha, lambda and delta. First of all, alpha. Alpha gives the curvature of the value function, which means when the value of alpha decreases, the curve flattens out. And the interpretation of it can be made like small changes may feel stronger. The slope of the graph, you can see it's steeper near x equal to 0 because of small changes. Then lambda. Lambda is the loss. Lambda is the loss multiplier. Experimentally, we found that losses hurt 2x more than like equal gains feel good. And as you can see from the graph of lambda, for the experimental value is lambda equal to 2.25. So losses hurt more in the gain. Then there's delta. Delta is which we used in the WP calculation. It's like humans, they underweigh the more likely events and overweigh the probabilities of less likely events, like a lottery.
So let's take a loss exit strategy, right? So say a gambler bets 100 rupees each round, and he exits and he stops immediately after his first loss. This creates a payoff distribution with many small wins, but one rare large loss. So here you can see x is equals the profit, right? So for example, you lose in the first bet, then your total profit is minus h. If you lose in the second bet, then it's plus h, then minus h, so it's 0, and so on. So it basically generalized to that formula, and the expected value of this formula is still less than 0, meaning the casino still wins. Here, you can see the graph, right? So the real large loss has probability 0.5, while the small wins have 0.25, 0.125, and so on, decreasing exponentially. So you are more likely to get a large loss than many small wins. Yeah. So how does CPT, the cumulative prospective theory, make a losing game feel rewarding? So basically, you can see this function, which there is a new term, right? This pi term. So basically, what happens is, so here the blue is the actual probabilities, while yellow is how we perceive them. So in the loss, we have 0.5 probability loss, right? But we are perceiving it, we are underweighing probability. So basically, what we're doing is we are making the negative term smaller, which will turn the whole thing positive, which will turn the VLE positive. And then in this area, with the smaller probability of winning, we are overweighing this probability, the small win. So basically, we are increasing the positive term, which is making the whole thing positive, meaning that we are perceiving probabilities differently. We are overweighing and underweighing the probabilities, and which is even though the expectation is negative, we still think it's profitable.
Now moving from psychology to mathematics. Once emotion drives a gambler to play, the only thing that controls the following is the mathematics behind it. Then the evolution of wealth can be modeled as a symmetric discrete random walk, where wealth is represented by a position x. So here you can, as you can see, xn plus 1 is the sum of xn plus yn minus 1 yn plus 1, where xn plus 1 denotes the denotes your position after n plus 1 bets, and xn is the position after n bets. Then y, you can imagine y is like, if you are at a particular position, then the probability of moving to the right is p, and moving to the left is 1 minus p. So, and y is plus 1 or minus 1. If it's a fair game, that is p equal to 0.5, it would be a symmetric random walk, and if it's less than 0.5, it would be a biased random walk, which would eventually lead to ruin. The variance of xn is it is a linear function of n. So basically, the risk grows exponentially, grows linearly with time n. And now, if we simulate this random walks for 6 different gamblers, we can see it's in the name, like it's random only. Some will go up, some will go down.
So this takes us to the gambler ruin problem. Like, how will a gambler go bankrupt? So let's start the gambler with initial bankroll K, and his goal is to get to n position, like get to n position. And each toss, let's say it's a coin toss event, and we're tossing a biased coin with probability p for plus 1 and q, which is 1 minus p, for minus 1. Now the situation is, it will stop if x equals 0, which is the gambler goes bankrupt, or x equal to n if it reaches its aiming amount. Now we want to calculate the pk, which is probability that the probability that he'll go ruin, given that he's starting at the position k. So yeah, so the toss follows this equation, which has boundary conditions as p not equal to 1, meaning if you're at position 0, you have already lost, you're bankrupt. So the probability of ruin is 1, and p n equal to 0, meaning you have already gone to your aim state, so the ruining probability is 0. When you solve this equation, you get this piecewise function where when the event is equal, when p and q are equal, you get pk equals 1 minus k by n. Yeah. So as you can see, as your bankroll increases, as the starting wealth increases, the ruin probability decreases. Meaning, if k is larger, then you can play more bets than if your k is longer, smaller. But anyway, eventually you will go bankrupt. So as I said, as n tends to infinite, as you can see in this equation, as n tends to infinite, 1 minus 1 by k by n will go to 1, meaning ruin becomes certain. And even in a fair game, infinite play guarantees bankruptcy. So let's simulate this. So yeah, let's follow a random walk and let's simulate 4 gamblers. 3 will have finite capital and 1 will have infinite. So as you can see in the simulation, 3 of the gamblers went bankrupt over increasing number of bets, but the one with infinite bankroll didn't. That means, given we have a constraint on a bankroll, we will go bankrupt. Yeah, so till now we have seen why people gamble and why we shouldn't gamble at all. I mean, yeah, every fair game we will lose. Finite wealth means certain bankruptcy, and expected value is less than 0, meaning the house always wins. So yeah, the mathematical way, the rational way is to think is to not gamble. But what do we do?
But what is the human reaction? I should just stop after 1 win. Maybe I should just double my bet. Maybe I should just follow a pattern. This is where randomness ends and strategy begins. Now, can you ever lose if you keep doubling? Suppose you bet 100 rupees on red on roulette, you lose. Next round you bet 200, you lose again. Next 400, you lose again. But when you bet 800, you win 600 rupees. you recover all your losses from the previous rounds, and then in the end you gain a profit of rupees 100. Now, how it works? You start with a base bet B0. You double after every loss. So, after each loss, your function will be 2bn, and after every win, it will be reset. It will be reset to B0 again. You always be in the end. Seems flawless, right? It always guarantees rupees B, but here's a small part we ignored. You can run out of money.
Yeah. So the thing is, when you go on a big losing streak, you might your whole bankroll might go bankrupt. So basically, the bets, right? They are increasing exponentially. So basically, total loss after n consecutive losses would be b to the power 2n minus 1. The next bet will be b into 2 to the power n, meaning your bet are increasing exponentially. So if you go on a big losing streak, you might just run out of your whole bankroll, and you won't be able to recover your money. Yeah, so as you can see, the bet function, the bet goes exponentially with loss count. So if you go on a big losing streak, you might just run out of your whole bankroll, and you won't be able to recover because you don't have money to double and win. Now this is a very simple pseudocode. What it basically does is it checks if your balance is greater than 0. If it is, then it see if you have winning or losing. If you win, it resets your bet and then increases your bankroll. If you lose, it doubles your bet amount and it decreases your bankroll. And this loop will go until your balance is less than 0, or you get through all 100 base bets. So now let's simulate this. Let's take 4 gamblers, and each starting with 10,000 rupees, 100 base bet, and a biased coin flip with probability 0.49 for the win. The play continues until either you are bankrupt or you go through all 100 bets. Now as you can see, some streaks look profitable, but gambler collapse, right? So as you can see the whole on the dips, right? So these dips are basically going through loss streaks. So as you can see the red graph, it's going up. It's having some dips, but it's going up. But eventually, for one time, it's going on a big losing streak, due to which it lost all of his bankroll, and it decreased to 0. Meaning only one losing streak it takes to make you bankrupt.
Now we'll prove how mathematically you will go to bankruptcy. So after after streak of n loses, what you get is the loss of b into 2 raised to n minus 1. Now when this ln term exceeds your current balance, you will go bankrupt. If the ruin probability will approach 1 if p is less than 0.5, because of the expectation value, you can see that it's negative for p less than 0.5. As number of rounds goes to infinity, that means as long as you keep playing, your ruin is certain. Here's an example. If you get suppose 7 consecutive losses, the probability of getting that is about 0.8%. So you can assume like roughly 120 average 125 sequences, you lose everything. So like after every 125 sequences, you are losing everything. So if you keep increasing your number of bets, your ruin is guaranteed. Now after losing many amounts of money in using martingale, the gamblers decided to flip the logic. What if we, instead of doubling after a loss, we double after a win and take advantage of the long winning streaks? Now suppose you bet 100 rupees on red and you win. Next round you bet 200 and you win again. Next you bet 400 and you win again. Now after 3 consecutive wins, you would cash out your money, you would back off and reset your bet to 100 rupees to take advantage of the winning streak of 3. mathematically you can see Bn plus 1 is a piecewise function of 2Bn and B0. You will reset to B0 if you get a loss or 3 consecutive wins. You only increase your bet after a win. So basically by doing this we are exploiting winning streaks and recovering from our profits and losses.
Yeah, but can this beat the system? Can a win streak beat probability? Yeah, so let's get into some mathematical terms. Yeah, so say you start off with 3 wins, right? So the expectation would be p to the power 3 and like this term. Okay, so let's take p equal to 0.49 and you put in p in the expectation value and we can still get negative term, meaning still the casino wins. It feels good, but the math still gives a negative expectation. This is the pseudo code. It's very basic. Basically, you just increase your bankroll when you win, increase the bet amount by twice amount when you win, and you reset when you have 3 consecutive wins or when you lose, and it goes till either you are bankrupt or all 100 bets are done. So here's a simulation of this. Now you might think that we are winning, right? I mean, we haven't still gone bankrupt. But as you can see, the thing is, when you lose, you make your bet, you set your bet to be not. So it's decreasing linearly. It's not decreasing in exponentially, that's why it's decreasing linearly. So that's the reason why it still hasn't gone bankrupt. So, but if you see for the long run, say for 10,000 bets, here you can see most of them have gotten bankrupt before 2,000 bets. Meaning, eventually you will go bankrupt, even if it's any strategy. So what are the traps? What are the reasons we weren't able to make money from this? The first thing is the dependence on winning streak. Basically, what we're trying to do is we're trying to get as much win as we want, so we can increase our money exponentially. But getting 4 win streak is only 5.7% chance. Meaning, for the rest of the 94% chance, you will lose and you reset your bet. The second thing is you think you are having a momentum. Like if you win, you will keep winning. But the thing is, probability is memoryless. The probability will always be p. It doesn't matter how much have you won or lost from last times. So the momentum doesn't exist. It's just your perception. And then the final thing, which is obvious, the negative expected value. Since it's negative, we know that house will win. So on long run, you will lose money. So there's nothing you can do here.
As we have seen, doubling your bets wouldn't work. So gamblers tried something new. Like they thought for Fibonacci because they thought it's a sequence that is used even in nature. As you can see, this is the Fibonacci sequence, as most of you already know. Each number is the sum of the previous 2 numbers. You move 1 step forward after a loss, and if you win, you will move 2 steps backward. Suppose you start with 100 rupees, you bet, and you lose. Now you move from the first +1 to the another one. Then you bet again 100, you lose. Now you move to 2. Here moving to 2 means multiplying your bet with the number, Fibonacci number, that is 2. So now you bet 200 and you win. Then you will move 2 steps back and you will restart. This is the function bn plus 1 for this. As you can see, it's very simple. Then the code. In the first 3 lines, we are generating the Fibonacci sequence, and then we are initializing the balance and base bet, and then we are running the loop. That is the algorithm of like simulating the win with probability 0.49. And the loop will terminate if the balance will go negative or the bets are more than 50. Now we can simulate using the pseudocode we saw earlier. 4 gamblers each start with 10,000 rupees, base bet 100. Now, as you can see, all of them are going in profit for a very long time, and then suddenly one of them just faced a huge loss. That is the this function is also explosive when it may fall suddenly when you are even getting profit, and even the profits are very growing very slow compared to martingale and reverse martingale. The fatal flaw in this is, first of all, expectation value, that is always it will be negative for house edge. Then the bets increase linearly, not exponentially, so you can't recover your money fast enough. And the main thing that fails this strategy is we rely on past outcomes to predict our next bet, but that's not how gambling works. It's the probabilities of winning in individual events are independent, so it doesn't matter you lose your last game, you may the next probability of win will always be P.
So let's compare these three strategies. We are setting up with 10,000 initial capital, 100 rupees base bet, winning probability 0.49, and we are testing all the systems, martingale, reverse martingale, is also known as Parodi or Fibonacci. What we should expect in these graphs are martingale should have exponential exposure growth, and because of that it will ruin abruptly. Reverse martingale has controlled exposure, but it will go to a peak and then suddenly drop as well. Fibonacci should exist for the longest time because it is delaying ruin because it's so it's basically recovering the loss slowly. It's not recovering like Fibonacci, like martingale. It's recovering loss very slowly. So it should ruin very late, but yeah, eventually it will ruin. So this is the simulation with 10,000 bets. As you can see, the reverse martingale fails instantly. The martingale goes for the longest, and the Fibonacci also goes till martingale, but it also fails. But here you can see is in the martingale strategy, it went to 15x its initial bankroll, meaning it went from 10,000 to around more than 1.5 lakhs. But then suddenly it dropped. That means just one losing streak, it's all it takes. It's all it takes to lose and go bankrupt. So let's look at some of the applications of this martingale and all these strategies. Basically, these strategies are tied well with finance and machine learning, and we'll see how it is. So in machine learning, so let's take example of reinforcement learning. Say, in reinforcement learning means, say you have an agent and he doesn't know anything about the universe. You give him some information and he has to act upon it. If he acts correctly, you give him reward, and if he doesn't, you give him punishment. Right. So as you give him reward and punishments, eventually it will learn a lot, right? And eventually it will go to condition that its expected reward is equal to the reward he'll get later, meaning he has nothing more to gain. Yeah, so this is one of the this is one of the graphs of reinforcement learning. So basically, as you can see in the initial stages, it's learning, it's getting punishment, and it's getting reward. It's going slowly up, and eventually it will go in the straight line, meaning it can't learn anymore. So the reward is not increasing; it's going in a straight line.
Another one of its application is in finance. As you can see, in trading also, martingale condition could be used to ensure no arbitrage. No arbitrage means you can't gain a profit without risking any of your money. The equation is like this. It is a martingale equation. The R delta T term here denotes the amount of money you can get without risking any of your money, and PT is the profit, and FT is information term, that is whatever information you provide to the trading algorithm. To conclude it, we started with gambler struggles, why gamblers gamble and stuff, and now we have ended at how machines learn and how trading algorithms work. Thank you.
And these are the references to one. Hello. If you have any questions, go here. Go to the first slide. If you have any questions, you can ask us.
Thank you, Prince and Shubham, for that very analytical look at probability.
And last but definitely not least, we have the algorithm, the unsung hero of the modern internet, secretly deciding the order of everything you scroll, click and consume every single day.
Let's talk about page ranking. Take a query and the web returns billions of pages. How does it know which deserves to be first? Enter the genius of this algorithm.
It's the invisible logic that organizes the chaos of the internet and allows us to find exactly what we are looking for.
Please welcome Sri Charan and Jyotiraditya for their talk on the mechanics of page ranking.
Yeah, good evening everyone. Today we will be seeing page ranking algorithm developed by Google, like how it changed the search engine's algorithm. Yeah, so let's start. First we'll see what were the algorithms used before the Google's page rank algorithm. So earlier search engines like Yahoo and all, they used actually the keyword matching. They mainly relied on keyword matching. So what actually keyword matching does is it takes the user query and then it compares with the keywords from the particular, means all the web pages, and it actually counts the number of occurrences of that particular keyword in a web page, and more the number of matchings of the keyword in the web page, it ranks the page higher. So the page with more number of occurrences are ranked higher on the web. So but that's not always means that what the user requires. Well, let's say for example, user query is best coffee beans, means he wants to know the best coffee. So page A which contains recipes of different types of coffee, and that page contains the keyword coffee 10 times, and there exists a page B which contains actually the best coffee beans, but it only contains the keyword coffee 3 times. So here the web page A will be ranked above the web page B, but that's not what the user expects. And also there were other problems, like it mainly relies on keyword matching. So the people who want to artificially inflate their website, means to push their website to a higher rank, they just spam the keyword, popular keyword in their web page repeatedly, and that their web page might not be relevant to the keyword also. So it causes a lot of low quality web pages to be ranked above the actual above the actual pages which actually contain the relevant data. So user had to scroll through a long list of low quality pages. So our the question is to develop an idea to rank pages according to the their quality and how often people visit the page, like the traffic on that web page. So the idea is this algorithm was developed by Larry Page and Sergey Brin, the founders of Google. They realized that a web is connected and the entire web is connected, the pages are connected via links, and a link from one page to another can be seen as a whole. Like if let's say page A has a link to page B, so page A is referring to page B. It's giving it's considered as a vote. So first we'll see how these web pages are represented via graphs, directed graphs. So all the pages are represented by nodes. Here you can see A, B, C, D, and these directed edges are the links from a page to another page. Let's say this edge E1 is the link from page A to page B. So you can go from page A to page B via E1, but you can't go the opposite way from B to A directly. If you want to go from B to A user wants to go from B to A, he has to go to E through E3 to D, then he can go to A via E5. So this is how a web is represented using graph. So the basic idea is every web page can vote another page by linking it. So like here you can see the page B is linking D and page C is linking D, so it has two votes you can see. So a page with more number of incoming links, like more number of votes, is likely more important because more pages are giving a link towards it, means it may contain some relevant data, so they are referring to that page. So there is also a flaw in this, means here also people can artificially inflate their website by creating lots of other dummy pages and giving a link to their actual website. So their web page will have a lot of votes and it will be ranked higher. So we'll modify our definition. So a page is considered more important when the links to that page are also given by some other important pages. Like page will be considered more important if the links are given, votes are given to that page via other important pages. And as an example, you can see that if a student wants to explore a new topic, so and he asks to, means he wants to read a research paper in that topic, so he goes to a student or research assistant who is working in that field and also to a well-reputed professor. So he takes input from the both. So the student is more likely to follow the professor's decision. So in that way only, because here professor is a more important source than a student. So the weight for a professor is more. But the definition actually is the definition here you can see is a little bit circular, because to know that a page is important, you should know the importance of other pages. So it's a circular argument. So we'll first see how to get this, let's work on this definition. So the way to calculate the importance is using a random surfer model. So what a random surfer model is, let's say this is our web page, for example, which web pages A, B, C, D and E, and these are the links. So we will take a surfer and the surfer will start with a random page, means all pages are equally likely and he will start from a random page. Let's say the surfer chooses page B, then after choosing a page B may have different links to other pages. Like you can see here, there is a link to E and a link to D. So all the links from a web page where the surfer are equally likely, means we assume that the random surfer is not biased and all the links from the web page are equally likely. So here there are two possibilities. So then the surfer goes to E, while clicking the link and visiting the page, and then we'll repeat this process, and we'll also maintain a counter for every page, every web page, which counts the number of visits to that particular web page. So yeah, from here the surfer goes to A, then to C, E, D, B, A. So what we have to continue this process for actually infinitely large number of steps, and here we have only given the 10 steps. But what it does is, if we run this for very large value of n, the fraction of a particular page, actually particular page means the fraction of visits to a particular page upon total number of visits, come to a means the probability, the fraction becomes stabilized, and we define a probability of event A, like is the probability that the random surfer is on page A at any given time. We define it by limit n tends to infinity, number of visits to page A upon total number of visits. So why this and this gives us a stationary distribution for that way. Stationary distribution is like if we consider if you run this random surfer model for very large value of n, the probabilities will stabilize and you will get a almost constant value of probability for each page. So that probability tells that at any instant of time the user being on that particular page. So that's a stationary distribution or steady state distribution. So why probability is a good measure of importance? Generally a page by nature is more important if the users come to the page more frequently or the other important pages interconnect with that page, because it might have a links or reference to a more important pages, or it might contains relevant information to that particular keyword. So therefore steady state probability reflects how likely a user ends up there. So this is a basic intuitive idea. Then the mathematical proof will be given by friend.
Yeah, before going into the mathematical details, I would also like to add a point to what Sricharan said. This page ranking algorithm ranks all the web pages in the web, and when a user searches for a particular page, then all the related pages are collected and then they are sorted based on the ranks generated by this page ranking algorithm. And going into the mathematical details, I would like to state why a mathematical model is required here in order to tackle this problem. If you see, the problem is that when we are conducting an experiment, here the experiment is a random surfer model, and we get a different number of different outcomes, and each outcome is associated with a particular probability. Basically here we get a sequence of states in which a user can lie at any instant of time. And in order to make predictions over this sequence, for example, if we want to predict where the user would lie in a like where the user would be at any step, and if you also want to find the fraction of visits to a particular state when the user surfs the web for a very large number of times. And also, as Sricharan discussed, that probability is a good measure of importance, we need to calculate that stationary distribution. And in order to calculate the stationary distribution, we require this mathematical modeling. So for that, we introduce a concept called as Markov chains. I think this day, many of you have discussed about something related to Markov. So, what is this Markov chains? Basically, we have an experiment where we conduct trials infinitely many number of times, and each trial has set of possible events which are mutually exclusive and exhaustive. And the property that this Markov chain has is that any trial, the result of any trial would depend solely on the result of the previous trial. For example, let's say we've done n trials, then the result of the nth trial would solely depend upon the n-1 trial result and not on the possible sequence of results from the
first to n minus 2 trials. Now, going into the common terminology used in this Markov chain, we have states. Basically, I've said every trial results in a set of possible events. There, instead of calling them as events, we call them as states. And as we move from trial to trial, the results would change. And the shift from one result to another result is called as a transition. And given that you are in a particular, basically, if a trial results in a particular state, we say that trial lies in that state. So if a trial is lying in that state, then what is the probability or chance that the next trial would lie in a different state is nothing but the transition probability. So basically transition probability is nothing but the conditional probability. For example, if you see the graph here, it is basically a weighted directed graph and we have 5 nodes. Say if you are currently at state A, then this 0.60 basically tells that there is a 60% chance of moving from state A to state B, and this 0.40 basically says that there is a 40% chance of moving from state A to state C. And one thing I would like you to focus here is that if a state has n outgoing links, the sum of all the weights should be 1, because any trial can result in one of the possible states, right? So for A, the possible states would be A, B, C, D, E, and it has finite non-zero probability only to move from A to B and A to C. Hence they sum up to 1. Now, going back to the original problem, we'll try to model the web as a Markov chain. And Sricharan already discussed the networking idea, the graph-based idea for this. I would like to formalize this one. We know that web consists of millions and billions of pages which are hyperlinked to each other. So we consider web pages as states here, and the edges are the means of transition from one web page to another web page for the user, and the weights are as usual the transition probability of moving from one state to another state. Now I would like to construct a mathematical equation, an important equation, which thereby leads to an eigenvector equation, and from that we get the stationary distribution we are targeting from the random surfer model we've been talking. For that I would like to use the board. So basically if you see here, I would like to consider a small scale example where we have 3 nodes, basically 3 web pages, A, B and C. Basically this PAB represents the probability of moving from state A to state B given that user is in state A, and this probability BA is nothing but the probability or the chance that a user moves from state B to state A given he is in state B. So the rest follows the same. Now let me define the sample space first for this. The sample space here would be an infinite sequence, infinite tuple, where each element of this infinite tuple is one of the states A, B, C, and we represent it like this. And now defining the random variables. The random variable xi basically tells the state in which the user is present in the ith trial. So xi can be either A or B or C as the sample, like it can have only A, B or C because these are the only possible web pages he can traverse in. So basically this is a discrete random variable. Now we are mainly aiming in order to find this distribution. For this we will use something called as law of total probability, which is very familiar to everyone. So let's say I want to find the probability distribution of xn. That means the probability that a user lies in a particular state in the nth trial. So for this the equation would be probability that he would lie in state A, for example, in the nth trial, is nothing but probability that he would lie in state A in the n-1 trial, and from there he moves to state A itself. Basically that is PAA. Or in the n-1 trial, he can be in state B. Further the probability is Pxn-1 is equals to B. And from there, moving to state A is the conditional probability PBA. Similarly, he can be in state C in the n-1 step. So this is the probability, and from there he could move to A with the probability PCA, basically the conditional probability. Similarly, you could write equations for B and C as well. This is just basically I've said what I've told what here is written. Pij is the probability of user moving from ith state to jth state. Yeah, these are the equations. Here I have denoted pi n as the probability lying in state A at the nth step, and the rest notations are the same. So these are the three equations, and this system of equations can also be represented in a matrix form in this way. Yeah, in this way. This matrix PAA, PAB, this matrix is called as a transition matrix. So basically, writing this in the matrix form would result this equation, pi n is equals to pi n minus 1 into p. So given any initial distribution, we can get distribution at any particular step or at any particular trial. And as the initial distribution changes, the distribution at the nth step would also change. So now we have a possible sequence of distributions pi 0, pi 1, so on. Now we are mainly focusing on the part for very large n, that is for after a very large number of trials. If we observe that after a very large number of trials, the probability distribution changes negligibly, and basically it means that as n tends to infinity, pi n would tend to a probability distribution which has a special name called as stationary distribution, and this stationary distribution is our target in order to rank the pages. And Sricharan starting when he is discussing about the random sulfur model, this was the thing he was talking about. And it is obvious for one to get it out that does this pi n would always converge to, does it always converge, or, and we know, as I said, that for as initial distribution changes, the distribution at the nth step would also change. So if I take pi naught, let's say pi naught 1, which is a different distribution, initial distribution, it may converge to finally to a different distribution. Take any another initial distribution, it may converge to a different distribution. So in order to answer this all questions, we have a theorem called as ergodic theorem. Before that, let me formalize what does stationary distribution mean. Stationary distribution pi is nothing but, when you have a transition matrix P, it is a distribution nothing but satisfying this equation pi p is equals to pi. That means basically it is a left eigenvector with eigenvalue 1, and obviously summation of all probabilities in the probability distribution would result in 1. Yeah, the questions that I have raised just now and the theorem. The ergodic theorem. Basically the proof of this theorem is not part of this talk. I would like to just state this theorem. Basically before stating this theorem, I would like to also define few terms. Irreducible Markov chain and also the aperiodic Markov chain. What irreducible Markov chain says is that a user can move from any state to any other state. If a Markov chain satisfies this condition, it is said to be irreducible, or if it doesn't satisfy, it's called as reducible. And aperiodic Markov chain means that after certain point of time, the sequence of possible states he traversed would repeat. So basically he would be looping in the sequence of states. And what the ergodic theorem says is that if the Markov chain is well behaved, that means if it is irreducible and aperiodic, then it will have a unique stationary distribution. That means it will have a unique left eigenvector with eigenvalue 1, and it would converge to this eigenvector for any starting state. And Eigenvector is nothing but if you have a square matrix A, a vector V is called as left eigenvector. Basically, a column vector, a row vector is said to be a left eigenvector if it satisfies V vector A to be lambda A, and lambda is called the eigenvalue of that matrix A and the eigenvector. So here are the few examples of like irreducible aperiodic Markov chain. This is clearly irreducible in aperiodic because take any state and you can move to any other state, and similarly this is clearly irreducible because if the user lies in state S3, then he's he can't move to either state 1 or state 2. He will be looping here itself. So it is not irreducible, it is reducible. And here, if a person starts from state S2, then he is guaranteed that he will move to S1. From there he will move to again S2. So basically he is looping here, looping between these two states. And you may get a doubt that here there are only two possible states, then obviously he would be looping through only between those states. But I would like you to focus on these probabilities. If these are not 1, then there would be a finite non-zero chance of him self-looping at a state. That means if a user is at state 2, then he would have a non-zero chance of him being in that state 2 itself. So in that case the chain may not be periodic. So in that case it may satisfy ergodic theorem. And here I have given an illustration. Consider this Markov chain. Basically I have considered 2 web pages. This clearly satisfies ergodic theorem, that is it is irreducible and aperiodic. And the transition matrix for this Markov chain is this one, and our aim is to find the stationary distribution for this. So basically in order to find the stationary distribution, we can use 2 conditions in order to generate all possible equations and thereby finding the eigenvector. One equation would be this one, pi p is equals to pi, and the other equation is obvious, which is pi 1 plus pi 2 is equals to 1, because these are only the 2 possible states in which a user can lie. So solving this matrix multiplication, we get these 2 equations, and here you may get a doubt that we have 3 equations and 2 variables. So, but this will result in an answer because basically these 2 equations are linearly dependent. That is, both are the same equations. So essentially, they form a single equation. And from the other equation, pi 1 plus pi 2 is equals to 1, we get pi 2 is equals to 3 by 7 and pi 1 is equal to 4 by 7. So the eigenvectors 4 by 7 and 3 by 7, the column vector, is the stationary distribution for this particular Markov chain. And if you observe, clearly state A has higher probability, so it is more important than state B, hence it would be ranked 1. And in order to verify our results, we performed a small simulation and we would like to show that simulation also. We will show that one through VS Code, we've written a code. Yeah, this is the code that we've written, and this was a transition matrix, and what this does is that, as I said, we've considered this sequence pi 0 pi 1. It will compute this sequence and it will see whether the error with respect to the stationary distribution is less or not. That means there would be a tolerance. If the error is less than the tolerance, then it would be like a good convergence. And when I run this code for that particular Markov chain, what we get is that we get this this is a simulated ratio. That means on iterating for a very large number of steps, basically here it is around 1 lakh to 10 lakh, I do not remember the exact number, but it's a very large number of steps. After simulating for that many number of steps, we get the distribution to be 0.5697 and 0.4303. And if you see the error, for state 1 it is around 10 power minus 3 and for state 2 is also around 10 power minus 3. So basically it means that this is matching the theoretical value that we've got. And before going to this, do you think that this algorithm covered each and every aspect of did it cover every possibility? I would say no, because you must obviously get it out that we've imposed several conditions that the Markov chain should follow the ergodic theorem. That means it must be irreducible and it must be aperiodic. But in reality, web pages may not satisfy that condition. So we need to do slight modification for this. So before going to the modification, I would like to state two cases. One is the case of dangling nodes and the other is the case of rank sinks. Basically, dangling nodes are nodes that doesn't have any outgoing links. So basically, it is like a trap that gathers each and every user traveling through that Markov chain. So if any user surfs through this Markov chain and ends up being in one, then he cannot move from one to any other state. Basically, he gets stuck there itself. So basically, it is like thinking self loop with probability 1. So this is not a very good idea because this leaves the chance for inflating their own web pages. And the second is the case of rank sinks. Rank sink is basically nothing but it is something like the periodic one. If a user starts at 1, let's say he moves at 3, then there's a definite chance of him moving to 4. Again, from 4, there's a definite chance of moving to 3. So basically, the user self loops from 3 to 4, 4 to 3, thereby inflating this rank. Because we've said that importance is nothing but the fraction of visits a user makes. So self looping through 3 and 4 increases the counter for them, hence thereby inflating their importance. So we do not want this to happen. So what modification we will do is that, this slide actually is a thoughtful slide. I'll also tell why I've kept this one. Basically, the idea is that when a user is basically surfing through the web, and let's say he's a focused researcher, and after surfing for a long time he gets bored, so he starts searching for a meme. So basically what he did is that he randomly jumped from one page to another one, even though generally a research paper and a meme doesn't have a direct link, right? So he might have randomly jumped. So this random jump is the main idea in order to solve this problem. So basically, at any given state when the user is present, either he can do a random jump or he can directly follow a link. So let's say that we have theoretical values. This is called as damping factor and this is called as teleporting also. So if he is at a particular state, alpha is said to be the probability that he would follow a link, and for the teleporting the probability is 1 minus alpha, because these are only the two possibilities. So with this additional modification, we will see how the transition matrix would get modified. So if you see here, again using the same law of total probability, the probability that user lies at state in the nth trial would be as follows. In the n-1 step, he might have been in A, and from there, he has two options. Whether he can follow a link or he can do a random jump. So if he decides to follow a link, then for that the probability is alpha. And once he decides to follow a link, then from there moving to state A would be the transition probability PAA. Or then he might have taken the second option, doing a random jump. For that the probability is 1 minus alpha. And if he decides to do a random jump, and as we had 3 pages in our earlier case where we derived the transition matrix, he can uniformly jump to any one of the page. So probability of jumping to one of the page would be 1 by 3. So 1 minus alpha by 3. Or similarly he can be at B and he can do the same choices. So basically we get this equation. If you observe this one, in the transition matrix the only change would be between the values would get modified. Each and every value would be multiplied with alpha and would be added with this 1 minus alpha by 3. So the transition matrix would get changed to this form. Alpha P plus 1 minus alpha into E. Basically this P is the original transition matrix and this E is the matrix where each and every entry is 1 by 3. And this matrix has a very nice name called the Google matrix. I think it is kept because it was developed by Google. So yeah, this is the definition. Like these are the notations. So basically, in order to give an intuitive idea, what happens is that we know that sum of all probabilities at a particular step is 1. And as the user moves from one step to another step, the probability distribution changes. That means there is a flow of probability between the states. Somewhere the probability is decreasing, and that decrease is being added to the probability of the another state. So finally what happens is that as we go with large number of trials, the probability gets accumulated based on the importance of the pages. So yeah, after this I would like my friend Sricharan to talk about the modern relevance and also the summary of this talk.
Yeah, so modern relevances like where other places where the algorithms is used is like in recommendation systems to rank the products and videos or anything according to the user behavior. In social networks, it also helps to find the influential users or communities. In academic research, to rank the research papers, like the paper with more citations is to be ranked above. And in cyber security, it identifies vulnerable or high impact nodes in the networks. So I would like to summarize the PageRank algorithm. The PageRank algorithm actually models the web into a Markov chain, and where the pages are represented as pages represent states and links represent transitions. Steady state probabilities reflect the relative importance of pages, and the damping factor ensures that all the edge cases are taken care of. And this algorithm provides foundation for modern ranking algorithms. Thank you. Any questions? What was the first slide? Okay, photo.
So, what if there is a page which has no other pages linking to it? So, like, how do you determine the
Random jump by
Yeah, like I've discussed, if a page doesn't have any outgoing link, then definitely it does a random jump.
incoming?
Huh?
If a page doesn't have any incoming link, so how are you gonna rank?
Yeah, from a random jump you can come to that page, right?
Random jump means by
See,
typing a URL
yeah, like
directly.
Basically, if let's say a node is isolated such that nobody comes in here through a direct link. See, basically, if there is no incoming link, that means there is no direct link, but he can come from a random jump. So random jump basically covers all the possibilities.
Means the damping factor. If we
How are you going to determine the damping factor?
I think so. It is based. I do not know exactly, but I feel that there would be certain test cases, and from that test cases they might have determined that damping factor.
The damping factor is around 0.85. Means it's used around 0.85.
And are there any like other uses of PageRank algorithm other than like?
Yeah, sure. Like, see, in order to answer that question, basically, if you see, I would like to state the example given by Sricharan itself. This concept or this ideology is also used in order to rank the academic papers. That's called as journal citation factor, if I'm not wrong. What they do is that if a paper has many citations given by other paper, not just many citations, but citations from a very reputable paper, let's say a person from a Harvard University or Stanford University. So then the paper to which they cited, that paper's importance or reputation would also increase. So in order to rank the web pages, also it is used. So basically, if you see, there are many other places where this is also used. This is just one of the illustrations. And one of the things that that I find is that ideas are just everywhere present, surrounding, like in nature, surrounding us, but we are not that much well prepared, or there might be some individuals who can identify those ideas, then make a mathematical model, and then create outbreaking solutions. So I found this one very interesting. Like I found this from my past talks also, where I had a problem, and when I see a solution, I find this solution that I see it every day in my life, but I never get this one to be the solution for the problem that I'm doing. So I hope your question gets answered. Thank you.
Thank you, Sri Charan and Jyotiraditya, for a perfect final talk on the algorithm that structures the digital world we live in.
We now request Professor Pandurangan to come to stage and share words of wisdom.
Okay, so dear students, you might have participated in the previous editions and you have gone through the current edition. One thing that stands out in IISc is you may check with your friends in other institutions. I'm sure you have friends in IIT Bombay, Madras, other institutions, NIT. You can check that nowhere a third semester student would organize this kind of a workshop where the students go all out completely away from their irregular classroom assignment or work, read some advanced material, grasp the research ideas behind them, and then make a presentation out of that. A research scholar, if you look at the learning profile, he would be a postgraduate or completed undergraduation, means all aspects of computer science through formal courses, then masters, and in the PhD in a well-guided manner, a particular research topic discussed and then reading a lot of research papers. So when the research scholar makes a presentation of an idea, you can see that so much of experience is behind that. Whereas most of you are just from the school, especially the third semester students, hardly 1 year before you were a school student, doing very routine calculations and then solving problem and stuff like that. And not much understanding of anything. You might have read physics and other things, but may not be very deeply. You may not have that opportunity, but the teachers will probably explain a formula, solve some problem in magnetism, optics and all in physics and chemistry, some equation, math, routine computation, formulas, simplifications. If you have trained in JE, some more advanced, wilder mathematics, that's all was done. Getting into the great ideas, appreciating them and then making a presentation of them is usually the forte of research scholars. However, in IISc we are in a research ambience. The major difference between, if you look at the institutions in India, it falls into roughly three categories. You take TIFR, Harish Chandra Institute, IMSc kind of pure research institute. They don't have any other activity than research. And if you take institutions like university colleges, and they don't do any research. There's some ABC engineering college. They just, because the teacher will come and prepare you for the semester exam, university context exam. There somebody teaches, somebody sets the question paper, somebody writes, somebody corrects, somebody evaluates, and all kinds of things. So you have at one extreme, you have only teaching institute, only research institute. There are other institutes like NIT, IIT and others, they combine both. But in what proportion? That's where distinguishes these kind of institutes. So IISc is predominantly a research institute where coursework is also done. There are other institutions which are predominantly teaching where research is also done. But so this institute has got a distinct ambience factor. You have a lot of research labs and then stalwarts in research, people who have built the research activities for 20 years and 30 years in a topic, and they have their lab or research group. Okay, you take any faculty who is reasonably senior at associate professor or other level. You don't have to go to the top professor. Even they would have got 10 years or 15 years of experience on building a particular topic and a research group and so on. That's the ambience here. So, in order to benefit from such an ambience factor, it is important that you too join the crowd, learn deeply, take every opportunity to go outside the classroom activities and then do some advanced work. But that ability is not built in one day, because you have just done some basic courses in computer science, probably third course or fourth course in computer science. You don't even know full computer science. Expecting you to do some computer science research that covers various aspects at this stage is unreasonable. However, you have to move towards it to benefit from the ambience factor. Here also you can come and then routinely write the exam, get mark, grade, go back and then take a job and die one day. That's perfectly alright. Routine existence one can always have. But is it something exceptional we can do, taking advantage of the facilities and environment that you are in? Whatever your personal abilities are, if I put you in some ABC engineering college, come at 10 o'clock, go close and go back at 4 o'clock, no labs, nothing will be available. There will be 30 computers and all computer science done, and there will be standard examples they will work out in the class and then they run away. You don't have any opportunity to learn. Right. Whereas here, how do we take the mileage out of that? How do we take the mileage out of the big research activities that are going? It's important that you gear yourself up, build your abilities to do these kind of things. And it has to start earlier, because any research requires immersion, a long interaction and intimacy with a particular topic. It has to start early. If you start some research activity, let's say, I find IISc is an exciting research place, let me start, and if you do that in the 8th semester, you don't have a window of time that allows you to do anything deeper, which means you cannot benefit much. Whereas if you start the research at an early stage, you will have 2 to 3 years ahead of you. When you do each course, you have an opportunity to interact with the faculty and then learn something advanced and so on. So this acts as a starting point or a trigger for you to build a taste in research activity and research reading. The problem you are discussing need not be the actual final research that you will be doing or something like that. It's only you learn to do research here rather than, okay. So for example, for the last speaker, it's not that he is going to do research in Markov chains and web page ranking for the rest of his life. But what he has learned, what they have learned is reaching out to a topic that is never discussed by anybody in any classroom, read on their own, reach relevant references, consolidate, compare, distill the idea, extract the common wisdom, organize themselves, and this is research. This is research experience. Equipping yourself and build a competence in research. Right. Much like if you want to excel in sports, you have to go to the gym and then fitness must be improved. The same way, in order to build that research abilities, things that normally could be done for a successful research those kind of activities. We should have a training, experience, exposure and so on. By these kind of activities, you are exposed to such an experience. Therefore, this is a gateway for you to enable yourself to excel in research and take the advantage of the ambience factor, namely the IISc factor and IISc facilities, IISc faculty and IISc research groups and so on. So, start from this, make this as a good starting point. Right? Even the people who are not spoken, after seeing that your own classmates could go out and then do so much of thing, it should be act as an inspiration. For the people who have already done, a good starting point and a good experience you have already got. For others, this is a point of inspiration. Your classmate and then with whom you have been daily walking around and then thinking that he is an ordinary guy, suddenly he becomes an extraordinary guy coming to the stage and then talking of great ideas in breadth and length, and suddenly you see that a vast difference. You can do that yourself, not a problem at all. Therefore, anyone can do. All of you are, I have mentioned this also in the class, all of you are equally blessed with phenomenal brain power, thinking abilities, absorbing abilities. If you have a will, there is definitely a way. If you determine that I am going to learn this, I want to understand this, and then go all out, you will be able to do that. It's not that it is not something impossible. Right? You will have resources, you will have people to contact, you will have various support that are available in the system that you can realize your dream. But the point is that you should start somewhere and then do something, and nothing will come automatically. You can get a lottery and then probably you can get 1 million rupees or 5 crore, even without working for it. But without working for it, you can't understand even a single lemma. You have to take, read, understand, discuss, or know the application. There is nothing automatic in learning. Learning is learner-centric. Therefore, if you want to do research, want to excel, want to make a stamp of your existence, want to do something distinguished, outstanding, opportunities are there. Equip yourself to reach those heights. Use your intelligence, potential you have. Don't waste all your intelligence and the knowledge and the power that you have, abilities that you have on worthless pursuits, useless things. Right? Try to use as much as possible. And here are the examples. All the talks that I have been given are not by any big experts with 100 or 20 years of research experience. They are just school kids an year and a half back, and today they are talking of great ideas and then making a presentation in a research institute. Look at the transition and the jump. The transition between you think over your past. How different you are from your 11th grade days, from your 10th grade days. How different you are from your 6th grade day to the 7th grade day. Incremental, margin. You are not some more, that's all. Right? Whereas, now you see what you are, what is that you have achieved, how much you have jumped over, and with this potential, will you be able to jump further? Only time can tell the answer. Only your effort can take you to any distance that you are willing to go. Therefore, I personally see, when we started this event 5 years back, a campus, we had undergrad, only undergrads, a very small 40 students, faculty, chit-chatting with the students and then interacting and other things. And, hey, why don't we do something really extraordinary and then do something about it? I taught something in the class on puzzles and paradoxes, and then can this paradox itself can act as a trigger for you to explore deeper and then go on, then let's have some conversation on this. And then, but then the enthusiasm of the first batch was so intense that the next week we have seen this paradox is very deep, this is advanced, that is, and then in a matter of few days, we thought it is a good idea to have even a kind of a workshop on paradox. And then we named it as a paradox festival, right? And then you can see the kind of talks that were given. I'm sure that is available even in the web somewhere. You can see the presentations. You can see the way in which they have articulated and understood and then ripped apart the basic puzzles. All third semester students. You will feel that they are some kind of a professionals who have so much of experience. No, they were just like you. When they were in their third semester, then when that happened, okay, naturally, when the next batch arrived, they can help, and then with more faculty help, the activities can grow, and in this way, we will be able to build. It's a legacy that is going to be set. It's not just an activity, it's a legacy that is set to influence the minds of the students, to tell the students that you can do a lot more, to send a message across the entire batch, both speakers, listeners, and even the people who have not attended. It doesn't matter, they can go through the YouTube pages that are probably available. The message is very simple and clear. If you have inclination, if you have enough interest shown, if you put in sufficient effort, you can define your own path of excellence in whatever is the topic. Right? In fact, I wanted to make few things little more beneficial to the audience, and I suggested first to the organizers that can we take a thematic thing like quantum computing or game theory, anything, distributed systems, where it is systems or it doesn't matter. Can we take some trendy thing or blockchain technology and organize all talks in that, so that a sequence of talks on a particular theme, everybody will know a lot about at the end of the day. It was contemplated as a one-day program. At the end of the day, you would have listened to some 6 or 8 presentations by various people looking into various, but then it's thematic. Quantum computing, let's say. Right? What are all the quantum algorithms? How does the quantum computer works? And then what exactly is the difference between your usual computer and quantum computer? Why do they say it's a big threat? And then all kinds of questions you can answer, provided you take a particular theme. But then the feedback was a lot more interesting. No, it's very diverse. The interest, the speakers would not like to peg all of them down into one particular mode. And as you can see, the range of topics that were discussed by the students. It's amazingly broad range of topics. That shows anyone can take any line of research, and then if you put in effort, you can read more, proceed further, and then achieve interesting innovations and novel ideas. You can create ideas and write research papers. You can design new systems and so on. You can innovate, and then you can take up a particular idea, look into practicality, and maybe you can become an entrepreneur and or collaborate with an entrepreneur, and then the possibilities opens up by a huge range. Right? There is no restriction. I didn't dictate anyone to take any particular topic in all this one, completely voluntary, on their own. Who gave the topic to X or Y or Z, who are the speaker? Nobody. It's their own thing. I read it, I know this, I find it interesting, so let me go and read it. That's all you have done. The success of this doesn't belong to any faculty or any individual. The success completely belongs to you. It's you who made it, you who designed the topic for you, you organized it and other things. Therefore, proceed further from this. Okay? Keep your research interest alive. Keep the flame of curiosity, pursuit of knowledge. Okay? Target of excellence, targeting excellence. Make that as an attitude, inbuilt attitude. Transform yourself into a serious person who is after great ideas, knowing things, working towards the details and understanding. Anything you choose. It could be computational biology, it could be geometry, it could be page rank, discrete math, or it could be Byzantine agreement, or it really doesn't matter. Wherever you go. Whatever you choose, excel in that. Continue to do that, and that is the one-line message this workshop should convey to the students. That's all is the purpose, right? It's not that we are going to have anything by way of doing this activity, right? Think of the past 2 days, how it went on, and then how the whole thing, the atmosphere and the way in which. Therefore, it's very important that we take mileage out of these kind of thing. May this act as a trigger for you to progress in the path of excellence in whatever field you like, in whatever interest you have, right? Wherever you want to do, go ahead and then excel in that. That's all I would like to say. And any community-based activity cannot be a success unless there is a large scale participation. The one mild disappointment I have is the lack of participation in large numbers. It's a small community activity. It is not anything that is forced on you. There is no marks or attendance or grade or nothing in this kind. It's only a student activity generated by student, carried out by students. Everything is done by the students. Tell me what is that I have done in this, other than arranging the lunch, coffee and tea in this hall. I didn't do anything. Right? It's done by you. Why the community is not responding to its own activity? Right? Why there should be so much of indifference, and then I am not that much keen on this kind of an attitude. It should not be the case. This drifting away and then missing these kind of student generated activities is it's not in good taste. People should know how to leverage out of the activities that are around. Nobody will call you for a seminar. There will be only a poster in the veranda and the hall. When you find that seminar interesting, you have to go and then sit in the seminar and then learn. What is that expert saying? Okay? What is he saying about mysteries of mysteries? Okay? Institute colloquium, organized by people who call experts, and spend time on this constructively. Prioritize. In life, we will always have temptation, we will always have opportunities to do dumb things, and then the message to the people who have not attended is that, what is that you have done in these 2 days? Will that take you closer to any field medal or a Nobel Prize or something like that? Or is it something much more important than this? It could be. They may be preparing for exam, and there are many other. I'm not saying that you don't have high priority thing. But the point is that if there is a possibility to prioritize this, a priority should be accorded for this. A communal activity is to be supported, encouraged, learnt from that. When that happens, the benefit would be maximum. So that's all I would like to say. Once again, I would like to thank heartily for all the speakers taking efforts and reach out various topics, learn on their own in the very short duration. Probably the day in which you have conceived the program and the day of the program is not really, you have a big window of time. You do have classes, courses, assignments and various things are packed in this. In spite of that, somehow you could steal some clock cycle and then spend some time for this extra reading, and then you could present it, and that's a welcome move. And this is how you have to do. Anything extra, you must determine, you must decide, I am not interested in wasting time on this. And at the same time, I am not a person who would recommend you to become a bookworm and then indulge in learning all the time and other things. Definitely not. That's counterproductive. What all I am saying is that prioritize, mix things. Of course, you should have fun, you should have games, you should have outing, and you must with friends, watch movie and then have fun time and hearty laughs around. It should all be there as a part of life. Don't miss that. But at the same time, do not lose focus and then do not miss the golden opportunities that are available around you. Right? We don't know, a mechanical engineering student, how many mechanical engineering industries are around. Whereas IT, computer science, so many industries are around in Bangalore. What was the advantage that you have taken out of that? One thing that you can do, because you have a database as such, call people from industry and ask them to give some reasoned perspective. They will be delighted to come here and then address the IISc students. They are all waiting for the best brains to come there as, as employees and other things. Call the R&D guys and then call the guys and then say that we are the student forum and we want your talk on overview of whatever is latest happening. Call a company which is running a cloud computing software and other thing. He will be very happy to say what is the current problem he is working on, and then he'll be excited about sharing the time. The database community can organize invited talks of that kind to know what's happening outside the world. And you don't have to pay him anything. He's right in Bangalore and he will be very happy to come in his own car and spend time and then go back. You don't have to give any honorarium or anything. Just they will feel very proud to reach IISc. That's the situation. So make use of that. So in whatever way possible for you to learn and expand yourself, you should be able to do. It's only one of the forums. And I had another suggestion also, if we could organize these kind of events sometime in the first or second or third week of January, but decide everything about the program by the end of November, including the speaker topic. Everything is to be frozen, but the event is going to be same hall, same thing. But the thing is, you will have window of time in December to prepare and to discuss with your friends, and then you can do a lot of things, technical aspect. And once you come here, you can rehearse, revise, discuss, and then fine-tune it. And then third week, and the first 2 weeks, assignments won't have been there, and then not much exam, no fear of those kind of things. Just now the semester would have started, and then end of the semester, every course becomes intense, and then you will be loaded with so many other things. Therefore, a good time would be for these kind of extra research and advanced stuff is have free time for you to read extensively, which is possible in vacation, right? So decide by November end. By the time you go back to your home after the final exams, carry with you the plan, carry it out, come back and execute in January. All of you will feel more comfortable. Even the participation. Many others, they don't mind if there is a quiz or exam tomorrow morning. How will they be sitting here and listening to some research ideas, which it will affect their marks and performance. Whereas if you schedule it something like that, the participation will be lot more, will be there. You will find it more comfortable to prepare well for the speech and many things. We will iterate it, we will discuss about it, and I want this legacy to continue. I want the impact to last longer, and I want every one of you to excel in your pursuit of knowledge and interest. I wish you all the best. God bless you all. Thank you very much.
Thank you so much, Professor Pandurangan. Now I request Rishi to present a vote of thanks.
Good evening everyone. It's my pleasure and honor to deliver a vote of thanks on behalf of the database community in ISc. First of all, we'd like to express our deepest gratitude to Professor Pandurangan. Without your motivation, we could not have made this fest into a reality. And we're also thankful for your inaugural talk on proxy encryption. Also for arranging the logistics, including the lunch and snacks that we all enjoyed. We would also like to thank the Computer Science and Automation Department for supporting us with the venue, and also for the KIAC Centre for sponsoring us. We also extend our thanks to Professor Arindam Khan and Professor Chiranjeev Bhattacharya, who gave highly inspiring and insightful talks and have enriched our knowledge and sparked new ideas. Also, a special note of thanks goes to Pratik from the Quiz Club at IISc for partnering with us to host the Turing Trivia Quiz. We also acknowledge the fantastic job done by our hosts. Your great enthusiasm and anchoring skills kept the energy high and the program flowing smoothly. And to all the speakers, thanks for your amazing work and your expertise and your time and the effort that you put behind your talks. Last but not the least, my heartfelt thanks go to you, the audience, and those of you who are connected online. Without your presence, the celebration would not have been the same, and this entire event was only possible because of the endless hard work that was put in by the organizing team from Database. And I'm proud to say that the event has been a huge success. Thank you all once again.
Now, thank you, Rishi. Now is the time we finally announce the winners of the Turing Trivia. I request Palak to come onto the stage to distribute the prizes to the winners. Also, I request everyone to wait for a group photograph after the prize distribution.
Hold your breaths, for the winners are: the third prize goes to
Team Cup Manade. Team members are Abhilash, Jeshwant and Ashika.
the second prize goes to
Team Domain Contraction Limited Facts. Team members are Menak, Saumyadeep and Shankha.
Congratulations, hearties, congratulations. Hearties, congratulations.
Thank you.
This is for your
Yeah, take a picture.
Oh, you're
done?
Oh, you are done.
Winner, second.
and the first prize goes to
Team Star of Monte Cristo. Team members are Himanshu, Sai Srikanta and Kumar Aditya. Congratulations to all the winners and well done for all the participants.
Thank you. And with that, we officially conclude the talks and the lecture for the Database Annual Fest. We hope you have been inspired and learned something new. And now, this is your chance to continue discussions and meet new people. Kindly and an extended thanks to the Professor for sharing your words of wisdom.
So, I would like to give somewhat of an excellent thank you to Professor Pandurangan. He has sort of been the backbone of the BTech program at IISc. So I am a third year student, so I've been with him longer than many of you have so far. And so he has been with us from the very inception of this program. He has been the backbone of this program. And he has always been eager to motivate us to pursue our dreams further. You know, what I've noticed is that even at this age, I believe Pandu sir has turned 71 this year.
Yes.
Even at this age, he has this passion for research and this curiosity within him that somehow dwarfs all of us combined here. And yet he is willing to motivate us, he is willing to pass on the torch. And I think this is why we organize these programs, that whatever speakers came here, they lit themselves a candle of passion, and we hope that they were able to pass on some kindlings to all of you. Thank you so much, Professor.
Thank you.
Okay, thank you. This is your chance to continue discussions and meet new people. And kindly do join us for more new and exciting events held at Database. We anticipate your presence and participations. We have been
Raghavan
and Ovia. Have a great evening. Goodbye.